The Sun's atmosphere is vastly hotter than its surface. The visible surface of the Sun, known as the photosphere, has a temperature of around 5,500 degrees Celsius. However, just above it, the solar corona can reach temperatures exceeding 1 million degrees. This temperature difference presents a challenge to the basic principles of physics, which suggest that outer layers should be cooler than the layers beneath them. Typically, heat dissipates away from its source, not intensifies with altitude. Yet in the Sun's case, the reverse happens. This paradox has prompted the development of several theories, though none have yet provided a definitive answer. One traditional theory involves small magnetic explosions known as nanoflares. These events could release enough energy to continually heat the corona in localized spots. However, such explosions haven't been observed often, or with the necessary intensity, which prevents this idea from being fully proven. Another line of research looks into the role of Alfvén waves. These magnetic waves travel through solar plasma, potentially transferring energy from the Sun's lower layers to its outermost one. While the concept is theoretically sound in controlled lab settings, it remains uncertain if real solar conditions allow such energy transfers on a large scale. The physics involved is complex, and testing these theories in real conditions is a significant challenge. The Parker Solar Probe mission was designed to explore these types of phenomena directly. It's venturing into regions much closer to the solar corona than any previous probe. During its passes, the probe has detected oscillations in the magnetic field and accelerated particles flowing through the Sun's atmosphere. These findings support the magnetic theory, but we still lack the detailed data necessary for conclusive evidence. A major difficulty lies in the nature of solar plasma itself. Plasma is a state of matter where atoms are ionized, creating a mixture of electrons and nuclei. This medium reacts strongly to magnetic fields, generating instabilities and non-linear processes. Small variations in these fields can quickly escalate into more significant phenomena, making it tough to model accurately. Even today, computational simulations struggle to capture the full complexity of this dynamic environment. Additionally, the solar corona doesn't have a clear boundary. It extends millions of kilometers outward, giving rise to the solar wind, which continuously flows through the solar system. This solar wind affects every planet, including Earth, and fluctuations in it can disrupt satellites, power grids, and communication systems. Therefore, understanding the heating of the corona has broader implications, including potential technological security risks. Another crucial factor is the Sun's 11-year cycle. This cycle directly influences the intensity of the corona. During periods of heightened solar activity, the frequency of sunspots and mass ejections increases, causing the corona to become even more dynamic and hotter. This cyclical pattern strengthens the idea that magnetic fields play a pivotal role in regulating the corona's temperature, although the precise relationship between magnetism and temperature is still unclear. Instruments like the Solar Dynamics Observatory are essential for monitoring the corona's dynamics in real time. They capture images in multiple wavelengths, revealing rapidly changing structures. But even with these advanced tools, many phenomena remain too small to observe, making it impossible to directly confirm the theories currently in place. The gap between observation and understanding remains significant. The puzzle of the solar corona's overheating extends beyond our own star. If the Sun, the most studied star in our neighborhood, behaves in this way, it's possible that similar overheating occurs in other stars. This could affect how we interpret data from distant stars, where coronas may be invisible to the naked eye but detectable in infrared or ultraviolet wavelengths. A unifying theory for these occurrences remains elusive. In practical terms, the overheating of the corona directly impacts space weather, particularly during solar storms. These storms can interfere with satellites, pose risks to astronauts, and disrupt terrestrial electrical systems. Thus, understanding the physics behind the solar corona isn't merely a theoretical pursuit. It has significant real-world applications for forecasting space weather and planning space missions. Solar science has made incredible strides in recent decades, but the Sun, in all its proximity and visibility, continues to present paradoxes that remain unsolved. The gap between the Sun's surface and its corona is perhaps the most striking of these mysteries. It serves as a reminder that even the most familiar natural phenomena, like sunlight, are driven by processes that scientists are still striving to fully comprehend. As new probes and telescopes continue to study the sun, the question of what causes the corona to heat remains one of the greatest challenges in modern astrophysics. On a separate but equally intriguing note, Sedna is one of the most distant and mysterious bodies in our solar system. It follows an unusually elongated orbit, taking over 11,000 years to complete a single revolution around the Sun. At its furthest point, Sedna travels 1,500 times farther from the Sun than Earth does. Its orbit doesn't intersect with that of any known planet, and its origin remains a mystery. Traditional planetary formation models don't adequately explain how Sedna came to occupy its current orbit. What makes Sedna even more intriguing is its minimum distance from the Sun, which never brings it close to the gas giants. This suggests that its orbit wasn't shaped by internal gravitational interactions. Furthermore, it's hard to imagine that it could have formed so far from the Sun, where the density of material in the solar nebula would have been exceedingly low. These discrepancies point to the need for new theories to explain its presence. One bold hypothesis suggests that Sedna wasn't born in our solar system at all. During the first few million years of the Sun's existence, it likely resided in a dense stellar cluster. In such a cluster, encounters between young stars would have been more frequent and much closer. One of these encounters could have allowed the Sun to capture objects like Sedna from another protostellar disk. While gravitational capture is highly unlikely today, it may have been much more plausible during the early stages of the solar system's formation. In this context, Sedna would be an interstellar fossil, a visitor from another star system forever bound to the Sun. Another potential explanation involves the gravitational influence of a hypothetical planet located far beyond Neptune, Planet 9. This massive planet would have the necessary gravitational pull to perturb objects like Sedna, pushing them into eccentric orbits. However, this theory also assumes that Sedna was already positioned on the periphery of the solar system when such an event occurred. In either case, Sedna's origins remain shrouded in mystery, pointing to the existence of forces or objects that we have yet to discover. The trajectory of Sedna could potentially be explained by the presence of a hypothetical Planet 9, but this theory doesn't account for its origin. What makes Sedna even more intriguing is its reddish hue, which suggests a surface rich in complex organic compounds. This coloration is similar to some trans-Neptunian objects, but has unique characteristics of its own. However, the exact chemical composition of Sedna remains undetermined. If Sedna originated around another star, its surface materials may differ from those found in the rest of the solar system. This could make studying it even more valuable. Sedna isn't alone in its unusual orbital behavior. Other objects, like 2012 VP113 and Leleaku Honoa, follow similarly elongated, isolated paths. These objects form a distinct population, with common orbital parameters linking them. This connection suggests they might share a common origin or have been influenced by the same processes. Simulation models show that these elongated orbits can remain stable for billions of years. This stability suggests that Sedna's orbit was not recently established, but likely shaped in the solar system's early days, possibly before the giant planets completed their migrations. This long-term stability hints that Sedna could be a remnant from the system's ancient history. Despite the scientific interest, Sedna remains beyond the reach of current space probes, and no planned missions will be able to reach it in the near future. As a result, astronomers are relying on ground-based and space telescopes for observations. The Vera Rubin Observatory, currently under construction, is expected to discover similar objects, helping to map out the outer boundaries of the solar system. Sedna's existence challenges the idea that the solar system is a closed, isolated system. It suggests that there may have been gravitational interactions with other stars, and that the boundaries of our solar system are more complex than previously thought. If Sedna came from another star system, it would mean that the Sun has actively interacted with its stellar neighborhood, potentially leaving imprints on other objects as well. Thus, Sedna is a rare and valuable remnant, offering clues about the environment in which the Sun was born and the history of other now extinct planetary systems. Its orbit and composition may hold secrets from over 4 billion years ago. Understanding Sedna's origin is essential for understanding how planetary systems evolve in dynamic environments. In addition to the solar system's outer edges, Europa, one of Jupiter's moons, presents a unique and intriguing phenomenon. It glows in the dark, even without direct sunlight. Europa's surface is composed of water ice, marked by fractures and smooth areas. But scientists have recently discovered that the moon emits its own light, even on its dark side. This faint but consistent glow doesn't rely on solar illumination. Scientists have simulated Europa's conditions in laboratories, bombarding ice similar to that found on its surface with high-energy particles, and they observed visible light emissions. This phenomenon, known as radiation-induced luminescence, occurs when energetic particles from Jupiter's radiation belt collide with the salts and ice on Europa's surface. The glow is not a reflection of sunlight, nor is it caused by heat. It's the result of photon emissions, triggered by electronic interactions within the ice. The type of salts in Europa's crust influences the color of the glow, ranging from green to blue to white. This discovery is significant because it provides an indirect method for studying Europa's surface without needing physical contact. By measuring the glow in its spectrum, scientists can infer the composition of Europa's ice, which will be crucial for future missions like the Europa Clipper probe. The data from these missions will help identify areas of the moon that are richer in salts or other compounds. Furthermore, the nighttime glow may also indicate the presence of charged particles near the surface, offering more insight into how Europa interacts with Jupiter's magnetic field. Europa is located in a highly dynamic electromagnetic environment, where particles collide with its surface at incredibly high speeds, altering its chemical structure and producing the faint glow. This constant bombardment, combined with tidal forces from Jupiter, could be responsible for the internal heating of the moon. This heating is one of the key theories suggesting the presence of a liquid ocean beneath Europa's icy crust, a potential environment for life. The glow emitted by Europa is too faint to be seen with conventional telescopes on Earth, but probes equipped with low-light sensors will be able to detect it while in orbit. The variations in luminescence could help pinpoint regions with active geological processes, or areas where material is emerging from below the surface. The light emitted by Europa serves as a continuous signature of its physical and chemical properties, and this signature will be instrumental in guiding future investigations. Moons like Europa are not static. Their surfaces react, interact, and emit detectable signals. The faint glow is a subtle yet revealing indication that Europa is a dynamic and complex world, one that offers promising clues about the potential for life elsewhere in the solar system. Similarly, Saturn's North Pole is home to a perfect and stable hexagonal storm, a phenomenon that has baffled scientists since its discovery by the Voyager probes in the 1980s. This storm, which spans about 30,000 kilometers in diameter, more than twice the size of Earth, has 6 nearly symmetrical sides. It rotates in sync with the planet and has remained in the same position for decades. No other celestial body has been observed with such a well-defined and stable storm structure. Unlike typical cyclones, this hexagonal storm does not dissipate or change shape over time, which makes it one of the most persistent and enigmatic phenomena in planetary meteorology. Laboratory models and computer simulations have attempted to replicate this pattern. In experiments with rotating fluids, similar polygonal shapes emerge under certain conditions. These experiments may help explain the formation and stability of Saturn's hexagonal storm, but the exact mechanisms remain a mystery. The storm's stability, despite extreme environmental forces, continues to pose challenges for scientists trying to understand the planet's atmospheric dynamics. Saturn's North Pole hosts a peculiar and stable hexagonal storm that has intrigued scientists since its discovery by the Voyager probes in the 1980s. Unlike the typical unstable or short-lived storm systems found elsewhere in the universe, Saturn's hexagon persists for decades, rotating in sync with the planet itself. This suggests that the forces at play are more complex than our current models can explain. The size of the hexagon is enormous, with each side measuring over 30,000 kilometers, more than twice the size of Earth. The fact that this structure remains anchored and fixed over time indicates that it is part of a deeper, more stable atmospheric current. The Cassini mission provided the most detailed images of this storm, revealing that the hexagon extends deep into the atmosphere of Saturn. The storm's central vortex is turbulent and has an eye. Resembling hurricanes on Earth, but unlike our planet, Saturn is made entirely of gas. There are no oceans or continents. This central cyclone, along with the hexagonal shape, has baffled scientists. At Saturn's south pole, a different circular vortex exists, one that behaves like a traditional cyclone, which adds another layer of mystery. The contrasting polar storm structures suggest that Saturn's atmosphere behaves asymmetrically, raising questions about the planet's thermal and dynamic balance. The makeup of Saturn's atmosphere plays a role in the formation and maintenance of these storms. It is mostly composed of hydrogen and helium, with small amounts of ammonia and hydrocarbons. The interactions between these gases under extremely low temperatures generate complex circulation patterns. These reactions influence the density and viscosity of the gases, which helps maintain the sharp, defined edges of the hexagon. Infrared images also show that the hexagon extends into deeper layers of the atmosphere, indicating that its pattern is not just on the surface but spans several layers deep. While researchers continue to study the three-dimensional structure of the hexagon, the data from Cassini have been instrumental. Understanding how the pattern forms and remains stable could offer insights into the distribution of internal energy within Saturn and how its rotation influences long-term atmospheric behavior. Despite seasonal changes, the hexagon has persisted for decades, which challenges our understanding of atmospheric instability, particularly when compared to Earth's own weather patterns. Without a solid surface like Earth's, Saturn's atmosphere behaves differently. However, even this difference doesn't fully explain the precise geometric regularity of the hexagon. Some scientists suggest that the hexagon might be a standing atmospheric wave, which occurs when air flows create alternating pressure zones. Still, the scale and precision of Saturn's hexagon exceed what typical waves would create. The stability of this formation points to a balance of forces that we are still trying to quantify. Currently, no active mission is studying Saturn directly. With advancements in climate modeling and fluid simulation, new hypotheses are expected to arise. But for now, the hexagonal storm remains an enigma. The mystery of Saturn's north pole highlights the complex and dynamic nature of gas giants. It reminds us that even after decades of observation, some planetary phenomena remain impossible to explain with certainty. Jupiter, the largest planet in our solar system, has a unique energy balance. Unlike Earth, which absorbs more energy from the sun than it radiates, Jupiter emits more energy than it receives. The planet radiates nearly twice the amount of energy it gets from the sun. This excess energy does not come from solar reflection or internal radioactivity, which suggests that it originates from a deeper, hidden source within the planet. Jupiter is primarily composed of hydrogen and helium, neither of which is naturally radioactive, which rules out internal nuclear reactions as the cause of this excess heat. Instead, the most widely accepted theory is that Jupiter's internal heat comes from a process known as Kelvin-Helmholtz contraction. As Jupiter slowly contracts under its own immense gravity, the planet releases potential energy in the form of heat. This heat, left over from Jupiter's original formation, continues to escape even after billions of years, meaning the planet is still slowly cooling. While this slow contraction is the main theory, some models also suggest that helium rain could be another source of Jupiter's internal heat. As the planet cools, helium separates from hydrogen and forms droplets that fall into the planet's core. This process releases gravitational energy, contributing to the planet's heat output. Evidence for this comes from spectral analysis of Jupiter's atmosphere, which shows a depletion of helium in the upper layers, consistent with the idea that helium is sinking deeper into the planet. Direct confirmation of this theory is difficult, as no probe has yet descended deep enough into Jupiter to observe these processes. Most of our knowledge comes from indirect data and theoretical models. Jupiter's internal heat is not just a fascinating curiosity. It plays a crucial role in the planet's atmospheric dynamics. The energy released from the planet's interior powers its powerful jet streams, storms, and vortices. The Great Red Spot, for instance, might be sustained at least in part by this internal heat. The temperature gradient between Jupiter's internal layers and its outer atmosphere drives convection, creating weather patterns that extend thousands of kilometers across the planet's surface. The internal heat also influences Jupiter's magnetic field. As metallic hydrogen circulates within the planet's core, it generates a strong dynamo effect, creating the most powerful magnetic field in the solar system. This magnetic field traps charged particles and creates intense radiation belts, which are critical for understanding Jupiter's radiation environment. Without the planet's internal heat, its magnetic field might be much weaker or more chaotic. Jupiter's moons, particularly Io and Europa, are also affected by the planet's internal dynamics. While they don't receive direct radiation from Jupiter's internal processes, the planet's gravitational influence and tidal forces enhance the moon's own internal heating. This dynamic feedback loop shapes not only Jupiter but its entire system of moons. Jupiter's case is not entirely unique. Saturn also emits more energy than it receives. But among the gas giants, Jupiter's energy imbalance is the most extreme. It challenges the conventional models of planetary thermodynamics, showing that planets can hold and release energy over long periods of time. Understanding this imbalance is crucial for refining our models of planetary evolution. It reveals that gas giants are far more dynamic than we once thought, their interiors remaining active long after their formation. Studying these processes offers valuable clues about the history of our solar system and could provide insights into exoplanets beyond our own. Pluto, long considered a frozen, inert body at the edge of the solar system, has surprised scientists with its geological activity. The New Horizons mission revealed a landscape full of diversity and unexpected features. One of the most remarkable discoveries was the presence of mountains that float on solid nitrogen. These mountains, which drift slowly across icy plains, exist in a region called Sputnik Planitia, a large basin covered by a layer of frozen nitrogen, carbon monoxide, and methane. Unlike Earth's mountains, which anchor into solid crust, Pluto's mountains float atop a dense frozen sea, made mostly of water ice. These mountains are less dense than the nitrogen ice below them, allowing them to move over time. This is a process similar to icebergs floating on Earth's oceans, but with the roles of ice and water reversed. The process is slow, taking millions of years, but evidence shows that the mountains do migrate, leaving signs of movement across the surface. Their movement appears to be influenced by convection patterns in the nitrogen ice. This suggests that Pluto is not geologically dead. Despite its small size and distance from the Sun, Pluto still retains enough internal energy to drive surface changes. The source of this energy may be residual heat from its formation, radioactive decay, or tidal interactions. Whatever the mechanism, it challenges the notion that small bodies in the outer solar system are inert and inactive. The floating mountains on Pluto provide clues about its internal structure. Beneath the nitrogen plains, there may be a subsurface ocean or a rigid icy crust. Understanding how the surface interacts with the subsurface is crucial for refining our models of cryogeology. In this way, Pluto presents us with an unexpected complexity, and the discovery of these mountains highlights the dynamic and active nature of the planet, despite its location at the fringe of the solar system. High-resolution images from NASA's New Horizons mission have revealed some fascinating geological features on Pluto. These images show polygons and fractures across the surface of Sputnik Planitia, which are signs of convection and stress. Some of the mountains even seem to be aligned with these fractures, suggesting that tectonic and thermal processes may be at work beneath Pluto's icy crust. Even in the far reaches of space, geological dynamics are present, though they manifest in forms quite different from what we observe on Earth. The mountains on Pluto's surface are composed of water ice, a material that remains solid even at Pluto's extremely low temperatures. This ice forms ridges, peaks, and fault lines, interacting with the softer nitrogen ice beneath it. This interaction leads to flexing and displacement, creating a layered geological system. These features are more complex than initially expected and hint at an active, dynamic surface. The slow movement of mountains over time suggests that Pluto isn't a geologically dead world, but one where subtle processes continue beneath the frozen exterior. Pluto's thin atmosphere may also play a role in shaping its surface. It undergoes seasonal changes that affect temperature distribution. As nitrogen sublimates and recondenses, it alters the pressure and flows of ice. These slow atmospheric cycles likely contribute to the movement of Pluto's mountains over time. The floating mountains were not predicted before the New Horizons mission, and their existence highlights how exploration can reveal planetary processes that go beyond what we know on Earth. Even distant dwarf planets like Pluto can surprise us with their active features. Rather than being a static body at the edge of the solar system, Pluto is a world of frozen complexity and quiet persistence. Its mountains move slowly and silently, telling a story of an ongoing internal exchange between solidity and plasticity, a balance formed by ice and time. Mimas, one of Saturn's smallest moons, has long been considered geologically inactive. The heavily cratered surface, dominated by the massive Herschel impact crater, seemed to confirm this view, but recent data challenges this perception. Measurements of Mimas's orbit and rotation have revealed tiny wobbles, known as librations. These variations suggest that the moon's interior is not entirely solid and may contain a liquid layer beneath its icy crust. These librations can only be explained if there is a global ocean beneath the surface of Mimas, transforming it into a potential ocean world. The idea of a subsurface ocean challenges the moon's previously assumed inertness and reignites interest in worlds once thought to be dead. Unlike moons like Enceladus, which show visible surface activity like geysers and thermal hotspots, Mimas has no such features. Its surface appears cold and thick, with few signs of resurfacing, suggesting that if an ocean exists, it is buried deep and isolated. If Mimas does have a subsurface ocean, it would be one of the smallest known moons to harbor liquid water inside. The primary source of heat keeping this ocean from freezing would be Saturn's strong tidal forces. Mimas orbits very close to Saturn, experiencing intense gravitational interactions. These forces generate internal friction and heat, enough to prevent the water from freezing entirely. It's a process similar to what happens on Enceladus, but likely occurring on a much subtler scale. Models suggest that Mimas's ocean would be relatively shallow, perhaps only a few dozen kilometers deep, but its existence would be remarkable for such a small, seemingly inactive moon. This discovery would expand the list of potentially habitable environments in the solar system. Even without signs of life, the presence of liquid water makes Mimas an exciting target for astrobiology. Its ocean might not be ancient, but could have formed less than 25 million years ago, which is young in geological terms. This could explain why Mimas has no obvious fractures or plumes, signs that might come from older oceans. If the ocean is young, it might not yet have left visible marks on the surface. Mimas's stable-looking surface may actually conceal a dynamic, unfolding story. In the future, we may see new fractures or cryovolcanic features revealing hidden heat sources. The potential for a subsurface ocean on Mimas holds significant scientific implications. If a small moon like Mimas can sustain an internal ocean, other similar-sized moons might also have the necessary conditions for liquid water. This broadens the criteria for habitability, suggesting that tidal heating and internal dynamics might be as important as size or surface temperature when considering the potential for life. Its future missions, especially Saturn orbiters, could test this hypothesis. Detailed measurements of Mimas's gravity and magnetic fields might be able to detect hidden liquid layers beneath the surface. With high-precision instruments, Mimas could become a priority target for future exploration. The potential ocean beneath Mimas emphasizes the idea that liquid environments aren't exclusive to large planets. Small, distant moons can also harbor subsurface oceans under the right conditions: enough ice, some internal heat, and time. This realization shifts our perspective on the complexity of smaller celestial bodies. Mimas may look like a plain, frozen moon on the surface, but it could be hiding an active geological process beneath that has been invisible up until now. The potential for life in such environments is just one example of how much lies beneath the surface of our solar system's most overlooked worlds. In the case of Enceladus and Dione, two of Saturn's moons, recent findings suggest they might share a subsurface ocean. Enceladus, with its active geysers and confirmed underground ocean, has been a focus of scientific interest for years. However, New data suggests that Dione, its larger neighbor, may also be part of the same interconnected water system. Gravitational anomalies detected by the Cassini mission indicate that both moons have internal regions that are less dense than expected, which could be explained by subsurface liquid cavities. If these cavities are connected by deep fractures or channels, they might form a shared hydrological system between the two moons. The concept of an interconnected ocean between Enceladus and Dione is unprecedented in the solar system. It would require a very specific orbital arrangement with a gravitational resonance between the two moons. This resonance would help maintain enough internal heat to prevent the water from freezing completely, and the gravitational interaction would keep the liquid in motion, creating a dynamic system of fluid flow between the moons. This type of interaction between moons is a new and exciting possibility for planetary science. Both Enceladus and Dione are rich in water ice, and their interiors contain rocky cores, along with salts and organic compounds. These ingredients suggest that their water is chemically active, rather than just a frozen liquid. If these moons are connected through an internal ocean, the exchange of compounds between them could create chemical gradients that support complex reactions, increasing the chances of finding habitable niches in the subsurface environment. The geysers on Enceladus release water vapor, ice particles, and organic materials into space, some of which fall back to the surface. Dione could be receiving or influencing some of this material, which would have major implications for the thermal dynamics of the system. Dubaiderma, despite lacking active geysers, shows evidence of past geological activity with tectonic faults and smooth surfaces. It may have been geologically active in the relatively recent past. If enough internal heat remains, the fissures linking Degeysen to Adelis could transmit pressure and warmth, potentially reactivating internal flows or opening new regions of geological weakness. The idea of a shared ocean between Enceladus and Degeysen has profound implications for astrobiology. A common reservoir of liquid water would offer a more stable and larger volume of liquid, creating favorable conditions for chemical reactions that could support life. The concept of interconnected oceans between moons is transforming our understanding of celestial bodies in the outer solar system. These moons may seem small and frozen, but beneath their icy crusts, they could be hiding vast, dynamic environments. The more we discover, the more we realize that the potential for life in our solar system could exist in places we never thought to look before. Even in the absence of sunlight, life, if it exists, could still have access to a vast, energy-rich network deep beneath the surface of celestial bodies like Enceladus and Dione. This idea, although speculative, is supported by current data, and future missions could test it with more advanced instruments. Tools like seismic profiling, orbital spectroscopy, and high-resolution gravitational mapping will be essential in confirming the possibility of interconnected subsurface oceans between these moons. Simply proving that Enceladus and Dione share a common ocean would be a groundbreaking discovery, showing that oceans aren't restricted to a single body. Such a finding would completely redefine our understanding of planetary geodynamics. It suggests that moons, often seen as isolated satellites of their host planets, could be part of a much larger interconnected system, offering insights into how planetary bodies interact with one another on a deep level. This interconnectedness challenges our traditional ideas of moons as solitary entities orbiting a planet. In reality, they may form part of a collective internal system, a concept that could have far-reaching implications for exoplanet studies and planetary systems beyond our own. The possibility of a shared ocean also highlights the importance of tidal forces. Saturn's gravity, in conjunction with its moon's orbits, creates an environment where heat and structure are constantly reshaped. It's a natural laboratory for studying extreme thermal dynamics, organic chemistry, and even the potential emergence of life in the most unexpected places. If Enceladus and Dione are indeed connected by a common ocean, it would expand the boundaries of what we consider to be habitable environments. Even in the coldest, most distant parts of our solar system, liquid water could still flow and interact across worlds, offering a new perspective on habitability in the universe. It's a reminder that our solar system still holds hidden structures waiting to be discovered, and sometimes two seemingly separate worlds have much more in common than we ever imagined. Saturn's rings are some of the most iconic features in the solar system, consisting of countless particles of ice and rock. But these rings aren't just beautiful, they are part of a complex dynamic system. Some areas of the rings vibrate in organized patterns, much like the vibrations of a musical instrument. These oscillations aren't caused by Saturn's moons but by the planet's own interior. The rings act as seismometers, responding to disturbances deep within the planet. This phenomenon, known as ring seismology, allows scientists to indirectly study Saturn's internal structure. The Cassini mission provided the detailed data necessary to understand these vibrations. By observing subtle changes in brightness and density in the rings, scientists were able to match the observed patterns to the frequencies predicted by models of Saturn's internal vibrations. These waves, especially those in Saturn's sea ring, amplify the effects of deep planetary activity, creating structures that echo the planet's internal dynamics. Saturn's interior is not static. It rotates at different speeds at different depths, a phenomenon known as differential rotation. This creates complex gravitational fields that influence the surrounding environment, perturbing the rings and creating a symphony of oscillations that ripple through the icy debris. Each oscillation in the rings is like a note in a cosmic symphony. These vibrations offer valuable clues about Saturn's core and inner layers. Models suggest that Saturn's core is diffuse, not solid, with a mix of rock, ice, and gas. The frequencies detected in the rings indicate that this core could extend up to 60% of Saturn's radius, challenging earlier assumptions that it was compact and sharply defined. This discovery opens up a new window into planetary interiors, allowing us to study a planet's inner workings in ways that direct observation cannot achieve. Not all the waves in Saturn's rings come from the planet's interior. Some are caused by resonances with moons like Mimas or Enceladus. However, the key difference lies in the frequency and location of these waves. Waves caused by the planet's internal motions appear where no moons are influencing the rings. The regularity of these waves and their match with internal models confirms their origin. Saturn's rings are unique in this regard. No other planet offers such a detailed indirect view of its interior. While Jupiter lacks visible rings of comparable density, and the rings of Uranus and Neptune are faint and disorganized, Saturn's rings are dense, structured, and ideal for such measurements. They act not just as debris fields but as active sensors, capturing and recording the planet's internal dynamics. The analogy between Saturn's rings and musical instruments is more than poetic. Just as a violin resonates at certain frequencies, Saturn's rings vibrate in response to the deep acoustic modes within the planet. By reading these vibrations, scientists can hear the planet's interior, which becomes surprisingly tangible and precise. This concept of planetary acoustics shows that a planet's interior dynamics can be mapped by listening to the vibrations it generates. Through its rings, Saturn is playing a gravitational symphony that tells us more about its internal structure than we could have imagined. This discovery also illustrates the interconnectedness of planetary systems. A planet's internal motions can influence particles millions of kilometers away, blurring the lines between its atmosphere, gravity, and rings. Forces that are invisible on a large scale leave physical imprints that can be detected in structures far from the planet's core. The rings of Saturn serve as a medium through which the planet's unseen dynamics are expressed. These findings highlight the importance of long-duration space missions like Cassini. Only through sustained close-range observation can we uncover the subtle effects that shape planetary systems. Ring seismology is still a developing field, and as data analysis continues, new patterns and harmonics may emerge. Each discovery adds depth to our understanding of Saturn's structure, collectively composing a planetary symphony played by gravity and ice. Through these rings, Saturn reveals its inner voice, a silent vibration through the void that speaks volumes to those who know how to listen. In the space between Earth and the Sun, there are stable clouds of dust that might surprise you. Although this space appears empty to the naked eye, it is actually carefully structured by gravitational forces. At certain points in space, dust accumulates and remains stable for long periods. These areas, known as Lagrange points, are where the gravitational forces between two celestial bodies, like the Earth and the Sun, balance out. One of these points, located near Earth's L5 Lagrange point, has been confirmed to harbor a semi-permanent cloud of interplanetary dust. This cloud, trailing Earth in its orbit, forms a faint, diffused halo that doesn't orbit Earth directly, but maintains a relative position due to the gravitational balance between Earth and the Sun. This dust cloud, known as the Kordalski cloud, is incredibly faint and difficult to observe from Earth. Its presence was once controversial because it wasn't consistently detected. However, recent advancements in infrared imaging have made these clouds more visible. Scientists can now track the dust's location and density by studying the way it reflects sunlight in specific patterns. Unlike planetary rings, these clouds aren't dense or uniform. They're more like loose swarms of particles, likely originating from asteroid collisions or comet trails. The particles get trapped temporarily in the gravitational equilibrium of Earth's solar system. While some particles escape, new dust is continually added, creating a semi-stable accumulation that persists over time. The discovery of these clouds reinforces the importance of Lagrange points in space dynamics. There are 5 such points in any two-body gravitational system, but L4 and L5 are the most stable, capable of hosting objects or dust for extended periods. That's why L5 is used to place satellites and space observatories. In the case of Earth, this dust cloud quietly resides just out of sight. While it has little direct impact on Earth, it could pose challenges for future space missions. The dust could interfere with sensors or obscure faint astronomical signals, so understanding its distribution is important for planning spacecraft trajectories. These dust clouds also provide a natural laboratory for studying particle behavior and microgravity. By studying how matter coalesces, disperses, or remains suspended under gravitational constraints, we can gain insights that apply not only to the solar system, but also to astrophysics. Similar dust clouds could exist around exoplanets orbiting other stars, showing us that space is far from empty. Even in the vastness between celestial bodies, structures can form and persist, shaped by gravity, light pressure, and orbital dynamics. These fragile, transient formations are detectable, and their study offers rich scientific opportunities. Space is never as empty as it seems. Between Earth and the Sun, there exists a network of stable dust clouds that quietly shape the dynamics of our solar system. These clouds, while faint and invisible to the naked eye, influence the movement of light and the behavior of spacecraft. They don't shine, pulse, or emit radiation, but their presence reveals something profound about the universe. When positioned just right, even small amounts of matter can create stable, long-lasting structures in space, demonstrating the subtle balance of cosmic mechanics. These dust clouds serve as a reminder that space, although appearing vacant, is in constant motion, sculpted by gravitational forces that shape invisible forms. Some of these dust clouds may still be undetected, hidden by the glare of sunlight or the limitations of our instruments. As technology advances, we might discover more layers of structure within this cosmic dust, revealing an even richer understanding of how matter behaves in the solar system. The study of interplanetary dust is slowly unfolding, and the clouds between Earth and the Sun offer a glimpse into a more intricate, dynamic universe than we ever imagined. Triton, Neptune's largest moon, challenges our expectations in several ways. Unlike most of the moons in our solar system, Triton orbits Neptune in the opposite direction to the planet's rotation. This retrograde orbit suggests that Triton didn't form alongside Neptune but was instead captured by the planet's gravity. The question of how Triton survived its violent capture remains an ongoing mystery. Capture events are usually chaotic and disruptive, especially for large bodies like Triton, which is even bigger than Pluto. For Triton to be captured without being destroyed or flung away is extraordinary. Its retrograde motion strongly indicates that it didn't form in Neptune's gravitational field, but rather was a distant body, most likely a dwarf planet in the Kuiper belt, that was pulled in during a gravitational encounter with Neptune. Once Triton was captured, it would have had a highly elliptical and unstable orbit. Over time, tidal forces from Neptune and the Moon's proximity to the planet gradually circularized its orbit, transforming it from a chaotic path into the more stable orbit we see today. However, Triton's retrograde orbit still exists as a remnant of its violent origin. Its unusual motion causes long-term instability in Neptune's moon system, potentially destabilizing or even ejecting other moons. This may explain why Neptune has fewer large moons compared to other gas giants like Uranus or Saturn. Triton's arrival likely reshaped the satellite system, and it remains a curious survivor of that upheaval. Triton's unique capture history has left it with signs of ongoing geological activity. Voyager 2 observed geysers erupting from its surface, indicating internal heat. Despite its cold surface, which is covered in nitrogen frost, Triton's terrain includes features such as smooth plains, ridges, and possible cryovolcanic flows. These surface features suggest a complex internal structure that remains active. If Triton has or once had a subsurface ocean, it would rank as one of the most intriguing ocean worlds in our solar system. Triton's composition, which is similar to that of Pluto and other Kuiper Belt objects, includes nitrogen, methane, carbon monoxide, and water ice, supporting the theory that it began as a dwarf planet before being captured into Neptune's orbit. Triton's retrograde orbit also means that it is slowly spiraling inward toward Neptune. Eventually it will reach Neptune's Roche limit, where tidal forces will tear it apart. This process, although billions of years away, could create a temporary ring system around Neptune. For now, Triton remains in a stable yet doomed orbit. Studying Triton offers valuable insights into the dynamics of planetary migration and the violent process of moon capture. It shows us how large bodies can be pulled into new gravitational neighborhoods, and how these migrations can leave lasting marks on the systems they enter. Triton, in this sense, is both a fossil and a living reminder of the chaotic history of outer solar system bodies. It remains one of the most accessible captured Kuiper Belt objects, and offers a unique glimpse into the unpredictable nature of planetary systems. Beyond Neptune lies the Kuiper Belt, a vast region filled with icy bodies and minor planets. What was once thought of as a chaotic zone of scattered debris has revealed a surprising pattern. Many objects in the Kuiper Belt share orbital characteristics that align too precisely to be random. Their orbits exhibit similar inclinations, eccentricities, and orientations, suggesting the presence of an external organizing force. This alignment is not easily explained by Neptune's gravitational influence alone, especially in regions where Neptune's pull is weak. Simulations that only include the known planets fail to replicate this clustering, indicating that something else may be at work. The most prominent explanation for this phenomenon is the Planet 9 hypothesis. This theory proposes the existence of a distant planet, possibly 5 to 10 times the mass of Earth, orbiting far beyond Neptune. Its elongated orbit would be able to shepherd Kuiper Belt objects into these aligned configurations, similar to how a shepherd moon shapes planetary rings. However, Planet 9 remains an unconfirmed presence, as its existence has yet to be directly observed. The case for its existence is supported by objects like Sedna and 2012 VP-113, whose orbits are too distant to be influenced by Neptune alone. The alignment of these objects suggests that they are being perturbed by a gravitational force from a hidden planet. As more objects with similar characteristics are discovered, the statistical significance of this pattern continues to grow. The precision of these alignments is not a coincidence. It points to a structure that remains without an obvious source. Alternative explanations, such as self-organizing dynamics among the belt's objects, require unusual initial conditions and long timescales, making them less likely. Another theory suggests that the Sun was once part of a dense stellar cluster, and early stellar flybys could have shaped the outer solar system. However, these scenarios don't fully account for the current level of orbital order observed in the Kuiper Belt. The clustering of objects with similar tilt angles and orbital eccentricities further supports the idea that an external force is responsible. If Planet 9 exists, its gravity could eventually eject some objects from the Kuiper Belt entirely, while others might become locked into stable orbits through gravitational resonance. This theory could help explain the gaps and voids observed within the belt, where fewer objects exist. Detecting Planet 9 is difficult due to its distance from the Sun and its faintness in the sky. Current surveys may not have the sensitivity needed to find it, but upcoming observatories like the Vera Rubin Observatory are expected to improve our chances of detecting this elusive planet. If Planet 9 is discovered, it would drastically change our understanding of the solar system. The outer regions would no longer be seen as marginal. Instead, they would be central to our understanding of planetary evolution. The Kuiper Belt would transform into a natural laboratory for studying the forces that shape planetary systems. Even if Planet 9 does not exist, the orbital patterns in the Kuiper Belt remain real and demand an explanation. These patterns suggest that the outer solar system is not a random debris field, but a dynamically structured region. Whether or not Planet 9 is found, the Kuiper Belt holds valuable clues to the cosmic processes that govern the formation and evolution of planetary systems. As our technology improves, we will continue to uncover the mysteries hidden in the farthest reaches of the solar system. Out at the furthest reaches of the Sun's vast domain, a fascinating symmetry arises from chaos. Whether driven by some hidden planetary force or ancient cosmic interactions, this phenomenon teaches us that order can emerge from the most unlikely of places. Hyperion, one of Saturn's moons, tumbles through space far from predictable. Among Saturn's many moons, Hyperion is particularly intriguing for its erratic behavior. Unlike most celestial bodies which rotate with a steady, predictable rhythm, Hyperion's spin is anything but consistent. It doesn't rotate smoothly. Instead, it tumbles unpredictably, its behavior governed by a chaotic spin that defies even the most sophisticated models. This irregularity means that, despite our best efforts, its orientation over time cannot be accurately predicted, even with the most advanced measurements. It's one of the rare moons in the solar system that exhibits this type of motion. Hyperion's unusual spin is largely due to its shape. Rather than being spherical like many moons, it's more elongated, resembling a giant potato than a typical round body. This shape affects how it interacts with the forces of gravity. Rather than spinning in a smooth, predictable manner, its uneven mass causes Hyperion to wobble erratically. This wobbling is made worse by the gravitational forces acting upon it, especially its interactions with Saturn and its moons, particularly Titan. Hyperion's orbit resonates weakly with Titan's, subtly influencing its motion over time. Though these gravitational interactions are small, their cumulative effect is significant. As Hyperion orbits Saturn, tiny changes in its motion continue to add up, leading to increasing instability. These forces cause a chaotic behavior that's extremely sensitive to even the smallest shifts. It was the Voyager spacecraft that first hinted at Hyperion's erratic behavior, but it was the Cassini mission that provided the first detailed evidence. By tracking Hyperion's orientation over multiple passes, scientists could observe how its rotational speed and axis shifted dramatically. The moon's spinning pattern could not be explained by conventional equations, which was an important clue to its unpredictable nature. The surface of Hyperion adds another layer of mystery to this chaotic moon. Its surface is deeply cratered, resembling a sponge or pumice stone. These jagged, sharp-edged craters are not simply the result of impacts. They are likely caused by Hyperion's extremely low density. The moon's porous structure causes impacts to compress, not scatter, the material, giving it an unusual carved appearance. Hyperion's low density also plays a significant role in its erratic motion. Unlike more compact moons which have internal cohesion that stabilizes their spin, Hyperion's mass is distributed unevenly. This means it lacks internal friction to help steady its rotation. While more solid moons naturally dampen their spin over time, Hyperion's loose interior allows its wobbling motion to persist. Each gravitational encounter only amplifies the moon's chaotic spinning, adding more momentum to its wild rotation. Despite this unpredictable motion, Hyperion remains firmly tethered to Saturn. While its rotation is erratic, its orbit follows a regular path. This distinction between its chaotic rotation and stable orbit is an important aspect of its behavior. It shows that even in the most unpredictable systems, some stability can still persist. Hyperion's chaotic behavior provides an incredible opportunity for scientists to study the intricacies of rotational dynamics. It's an ideal natural laboratory for observing how shape, mass distribution, and orbital dynamics influence motion. Hyperion stands as one of the most fascinating real-world examples of deterministic chaos, a system that follows natural laws but remains unpredictable in its details. Studying Hyperion's motion also helps scientists model the behavior of other small moons and asteroids. It's likely that many other celestial bodies have undergone similar chaotic phases. Some may have stabilized over time through tidal friction or collisions, but Hyperion, unlike most, remains stuck in this chaotic state, offering a snapshot of a dynamic that's lasted for millions of years. Despite its seemingly erratic behavior, Hyperion's relationship with Saturn is stable. Its orbit around the planet is predictable, even though its rotational movement is not. This illustrates an intriguing concept. Chaos and order can exist together. A chaotic system like Hyperion's doesn't necessarily lead to an unstable orbit, demonstrating that even in the most unpredictable systems, some degree of order can be maintained. Remarkably, all of Hyperion's dynamics are driven by its shape, mass, and gravity. No atmosphere or magnetic field is needed to create such an effect. This makes it an ideal system for testing physical models of rotational motion. Researchers continue to improve simulations of Hyperion's behavior, but long-term predictions remain uncertain. The Moon's behavior is inherently unpredictable, a characteristic that would make landing missions difficult. Any spacecraft attempting to land would have to deal with a constantly shifting surface. But in this unpredictability, Hyperion reveals fascinating insights into the nature of motion in space. It's a natural experiment in action, continuously providing new data without the need for any controlled environment. Hyperion stands as a unique outlier in Saturn's orderly system, a moon that doesn't follow the laws of predictable motion, but instead embodies perpetual disorder. This chaotic nature isn't just an oddity, it showcases the deep complexity of motion in the cosmos, reminding us that order and chaos are often intertwined. Neptune's magnetic field is far from ordinary. Its mantle dynamo generates an intricate and irregular field that sets it apart from the other planets in the solar system. When Voyager 2 passed by Neptune in 1989, its instruments recorded drastic shifts in the planet's magnetic orientation as it rotated. These shifts were too extreme to come from a perfectly centered symmetric magnetic field. Instead, they revealed a dipole that was not only tilted but also displaced from the center. The magnetic axis is located thousands of kilometers away from Neptune's core, making the field's behavior much more complex than previously believed. This magnetic offset has profound effects on the planet's magnetosphere. As Neptune spins, the field behaves like a wobbling top, sweeping charged particles along unpredictable paths. This motion distorts the auroras, creating shifting and asymmetric patterns of light. The result is a magnetic environment that is constantly evolving and difficult to model. This complexity suggests that Neptune's internal structure is more layered and multifaceted than we thought. One potential factor in this is the presence of superionic water, an exotic high-pressure phase of ice that conducts electricity. Though data on this material is scarce, it may be driving the planet's off-center dynamo by flowing in turbulent patterns. The tilted magnetic field also affects how Neptune interacts with the solar wind. Its magnetosphere doesn't behave in a predictable manner. Instead, it expands and contracts erratically, which could impact atmospheric escape or even the dynamics of its rings. Unlike Earth's uniform magnetic shield, Neptune's field provides an uneven protection, with some areas of the planet being shielded more effectively than others, depending on the alignment of the field and the planet's rotation. Looking to Uranus, we see that Neptune is not alone in having an irregular magnetic field. Uranus also has a highly tilted and offset magnetic field, suggesting that these ice giants may share similar internal structures or formation histories. Both planets seem to lack solid cores and likely have deep layers of convecting fluids. However, the exact details of these processes are still uncertain. Ice giants remain the least explored class of planets, and much about their inner workings remains theoretical. Neptune's magnetic field, with its peculiarities and irregularities, makes it a top priority for future space missions. A dedicated orbiter could map the field in detail, capturing its temporal and spatial variations. This data would significantly improve our understanding of dynamo processes, not just on Neptune but in other planets and exoplanets with similar characteristics. By studying the magnetic evolution of Neptune, we can refine our models of planetary formation, heat transfer, and atmospheric dynamics. shedding light on the fundamental forces that govern planets. One fascinating area of study is how Neptune's moons might interact with this chaotic magnetic field. Similar to how Jupiter's moon Io generates currents within Jupiter's magnetosphere, Triton, Neptune's largest moon, could cause disturbances in the magnetic field. These disturbances might create radio emissions or localized auroras, providing valuable insight into how moons couple with their parent planets in environments with asymmetric magnetic fields. Neptune's behavior challenges our assumptions about planetary magnetism. While planets like Earth and Jupiter have neat, aligned magnetic fields, Neptune spins with a tilted and displaced field. This stark difference broadens our understanding of the diversity of planetary configurations. The unique behavior of Neptune's magnetic field goes beyond mere misalignment. It's fundamentally different, offering a window into the varied and exotic nature of planetary interiors. Turning to Uranus, this planet too holds an intriguing mystery. Despite being overshadowed by its more well-known neighbors, Uranus harbors one of the most puzzling phenomena in planetary science. Its upper atmosphere is unexpectedly cold. The temperatures in Uranus's upper layers drop below 50 Kelvin, making it one of the coldest places in the solar system. This extreme chill cannot be fully explained by Uranus's distance from the Sun. In fact, it remains a major enigma. Planets generally absorb solar energy and then emit it as thermal radiation. This balance determines the planet's temperature, but Uranus doesn't follow this norm. Unlike Jupiter, Saturn, and even Neptune, which emit more heat than they receive from the Sun, Uranus seems to lack internal heat. It emits almost no excess heat, suggesting that it either lost its internal warmth or never had much to begin with. This absence of internal heat could be contributing to the freezing temperatures in the upper atmosphere. Without heat rising from the interior, the outer layers cool off more rapidly. But this alone doesn't fully explain the observed temperatures, as simulations that include solar radiation, atmospheric chemistry, and convection predict higher temperatures than those actually detected by instruments. The lack of heat could be linked to Uranus's unique axial tilt. This planet spins on its side with an axial tilt of over 98 degrees. This unusual orientation might alter how heat is transported within the atmosphere. Since Uranus experiences extremely long seasons, the Sun's energy is distributed unevenly, which could suppress convection or change atmospheric circulation. While this theory remains speculative, it could be a key factor in Uranus's thermal mystery. Another possibility is the role of aerosols or haze in the upper atmosphere. These particles might reflect infrared radiation, preventing heat from escaping, or they could absorb energy at certain wavelengths and re-radiate it inefficiently. Observations of methane and hydrocarbon hazes suggest such layers exist, but the precise thermal role of these aerosols is still unclear. There could also be active cooling mechanisms at play. Some scientists propose that specific molecular transitions in Uranus's atmosphere could radiate heat away more efficiently than expected, lowering the overall temperature. But once again, models are still uncertain, and further research is needed to confirm this. Uranus's deep atmosphere may also be contributing to the cold upper layers. If the lower layers trap heat more effectively than we thought, they could act as an insulating barrier, reducing heat flow to the upper layers. To confirm this, we need detailed profiles of the temperature and composition throughout Uranus's atmosphere, data that is currently lacking. The dynamics of Uranus's atmosphere are also poorly understood. Winds are high, and cloud patterns are faint and irregular, suggesting complex circulation patterns but without clear signs of convection. The absence of storms or vertical mixing suggests a more stratified atmosphere, further reducing heat exchange. All of these factors contribute to the planet's cold and stable upper atmosphere. Comparing Uranus to Neptune only deepens the mystery. Despite receiving similar solar input, Neptune retains more heat and has a more active atmosphere. Why Uranus lost its internal heat, while Neptune did not, remains one of the biggest puzzles in planetary science. Both planets share similar compositions, yet their thermal histories are starkly different. Understanding these discrepancies is crucial to refining our models of planetary evolution. Uranus's temperature mystery underscores the need for more dedicated exploration. A mission to Uranus equipped with spectrometers and atmospheric probes could map thermal gradients and track radiative processes in detail. This data would help refine our understanding of not only Uranus but also other ice giants and exoplanets with similar characteristics. Uranus may be an outlier, but studying its enigmatic atmosphere could provide crucial insights into the broader diversity of planetary systems. Titan's surface is a stage for some of the most intriguing chemical and geological processes in the solar system. Beneath the icy exterior, there is evidence of complex interactions between Titan's interior and its methane-rich atmosphere. Some scientists believe that icy lava, a mixture of water and ammonia, might erupt from Titan's interior. These eruptions could mix with the surface methane, renewing the surface in a continuous cycle. This interaction between the planet's internal processes and atmospheric conditions creates a dynamic and constantly evolving environment. Unlike Earth's oceans, Titan's seas are unlike anything we're familiar with. They're non-polar, non-conductive, and made of liquid methane and ethane, rather than water. The chemical composition of Titan's seas makes them dark, reflecting radar waves in a way that made Cassini's observations possible. The spacecraft detected gentle waves on the surface of Titan's seas, small ripples just a few centimeters high, driven by winds. These subtle signs of alien weather reveal a planet where liquid methane flows and evaporates just as water does on Earth, completing a cycle of methane-based weather. Titan's chemistry holds significant astrobiological interest. The atmosphere contains methane and ethane, which are hydrocarbons, and Titan's surface is home to complex organic molecules. Photochemical reactions in the upper atmosphere generate tholins, large organic compounds that fall onto Titan's surface. These compounds could be key ingredients for prebiotic chemistry, which might unfold in Titan's lakes, even in the absence of liquid water. This raises one of the most exciting questions: could life exist in methane? On Earth, life depends on water as a solvent, but Titan's methane environment might support life forms adapted to its unique chemistry. No evidence of life has been found on Titan yet, but it offers a natural laboratory for testing the possibility. NASA's upcoming Dragonfly mission aims to explore Titan's lakes directly. This rotorcraft will hop between multiple sites on the Moon, studying its surface chemistry, atmospheric processes, and the structure of the lakes. Titan's methane cycle also provides clues to early Earth. Some researchers speculate that Earth once had a thick methane atmosphere, and studying Titan could offer insights into what our planet might have looked like in its early history. It also has implications for exoplanet research, as planets with methane atmospheres may exist elsewhere in the universe. With surface liquids, a thick atmosphere, and organic chemistry, Titan is one of the most Earth-like bodies in the solar system, yet its environment remains profoundly alien. Its seas are bitterly cold, and its rivers are made of liquid gas. This strange duality makes Titan one of the most compelling targets for exploration. Beneath its hazy atmosphere, Titan presents a world shaped by exotic rain and rivers, a mirror to Earth reflected in methane, both familiar and unfathomable. Venus, Earth's twin, presents its own mysteries. Today, Venus is an incredibly hostile world, with surface temperatures soaring above 460 degrees Celsius, surrounded by a thick, CO2-rich atmosphere. However, models suggest that this wasn't always the case. Billions of years ago, Venus may have had a temperate climate, oceans of liquid water, and conditions that could have supported life. This dramatic shift in Venus's environment might have occurred relatively recently in its history. Climate simulations using early solar conditions suggest that Venus once had a much slower rotation and received less solar radiation, which would have allowed it to maintain surface temperatures well below 50 degrees Celsius. In this climate, liquid water could have existed, regulating the planet's climate through weathering and carbon cycling, just like Earth. Venus's highlands may have once hosted shallow seas, supporting a stable environment. Atmospheric measurements also support the idea of ancient Venusian oceans. The unusually high ratio of deuterium to hydrogen in Venus's atmosphere suggests that large quantities of water once existed on the planet. Over time, however, solar radiation and atmospheric escape processes drained most of Venus's water, What remains is a chemical fingerprint of the planet's once habitable past. Venus's relatively young geological surface suggests that the planet underwent a massive resurfacing event between 300 and 700 million years ago. Before this upheaval, Venus may have experienced volcanic cycles and plate tectonics similar to early Earth. If this is true, Venus could have supported stable climates for billions of years before its environment collapsed. What caused this collapse remains uncertain, but one leading theory is the loss of Venus's magnetic field. Without this protective shield, the solar wind may have stripped Venus of its water, dramatically altering the planet's atmosphere. As water disappeared, volcanic outgassing of CO2 accelerated, leading to a runaway greenhouse effect that transformed Venus into the scorching world we know today. Despite the hellish conditions on Venus's surface, the planet's upper atmosphere remains relatively temperate. At altitudes between 50 and 60 kilometers, the temperature and pressure are similar to those found on Earth's surface. This region has been proposed as a potential habitat for microbial life. If life ever existed on Venus, it's possible that it migrated to the clouds as the surface became uninhabitable. Recent discoveries, such as the possible detection of phosphine, a gas associated with biological processes on Earth, have reignited interest in Venus's potential for past life. Although the detection remains disputed, it has opened the door for renewed exploration of the planet. Venus, long neglected, is now a central target for astrobiological research. Upcoming missions such as NASA's Veritas and ESA's Envision will map Venus's surface and atmosphere using advanced instruments. These missions aim to uncover the planet's geological history, tectonic activity, and the possibility of ancient water. If Venus was habitable for billions of years, it would transform our understanding of planetary evolution, showing that Earth-like conditions might not be as rare as we once thought. This realization would change the way we search for life on exoplanets. A rocky planet with a similar size and mass could be another Earth, or like Venus, it could be an exoplanet with a hostile climate that was once habitable. Venus's story is a reminder that planets are dynamic, with their environments constantly evolving. What we see now may not be what has always been. Venus may have once been a second Earth, with oceans and a temperate climate, before its environment collapsed into the hostile world we see today. Its story is both a warning and a mystery, reminding us that planetary habitability can change over time. Venus, once Earth-like, now stands as a scorching relic of what might have been. At the Moon's south pole, a massive and unusual metallic anomaly has been uncovered, located about 300 kilometers beneath the surface, and stretching more than 2,000 kilometers in width. This buried mass is so significant that it causes a noticeable distortion in the local gravitational field. Its discovery raises crucial questions about the Moon's geological history and the dynamics of the early solar system. The structure was first detected using data from NASA's Grail mission, which studied slight variations in the Moon's gravity. These variations revealed a concentration of mass far denser than the surrounding crust, pointing to something hidden beneath the surface. The anomaly resides beneath one of the largest known impact craters in the solar system, which suggests that it might be linked to the impact event. However, the exact nature of this connection remains unclear. One theory is that the mass could be the remains of a metallic asteroid core, which, after a collision with the Moon, might have separated from the asteroid and embedded itself deep into the Moon's mantle. Over time, surrounding materials may have flowed around it, but the core itself stayed embedded within the Moon. If this theory holds, it would be significant proof of asteroid differentiation and the dynamic nature of massive impacts in the solar system. Another possibility is that the anomaly formed as dense oxides accumulated during the Moon's early magmatic evolution. As the Moon's magma ocean cooled, heavier materials could have settled, creating regions where these metallic oxides concentrated. These oxides might explain the mass's unusual gravity signature, although this explanation does not fully account for the specific shape or placement of the anomaly within the basin. The exact composition of the buried mass is still unknown. It may contain iron, nickel, or other dense metals, possibly in the form of a solidified alloy. While spectroscopic data from orbit provide some clues, they are not enough to confirm the composition. Ground-penetrating radar and seismic measurements would be necessary to probe the region's structure more directly, but for now, the mystery remains unsolved. The anomaly's influence goes beyond just gravity. It likely affects the surrounding crust's topography and stress patterns. The South Pole Basin, where this mass lies, is deep and elliptical, and the mass beneath it could explain why the basin didn't rebound fully after the impact. The mass could also affect nearby fault lines, crater formation, and the distribution of regolith. Understanding this anomaly is important, not just for lunar science, but also for broader planetary formation theories. It serves as a real-world example of how massive impacts shape celestial bodies, and could also offer insight into other lunar impact basins and similar features on other moons and planets. This discovery makes the moon an exciting target for future exploration. Missions could send seismometers or electromagnetic sensors to study the anomaly in greater detail. While drilling into the surface would be a challenge, robotic platforms might be able to reach the upper edges of the buried mass. Investigating this anomaly could provide valuable samples from deep within the moon or even remnants from the core of an ancient asteroid. Some fringe theories even suggest that the mass could be of artificial origin, though there is no data to support this claim. Nevertheless, the size and density of the anomaly have captured public imagination, highlighting how much we still have to learn about our nearest celestial neighbor. From a scientific standpoint, the anomaly reinforces the idea that the moon's interior is more complex than previously thought. It's not a simple uniform ball of rock, rather it exhibits heterogeneities that point to a dynamic history shaped by heat flow, magma movement, and impacts over billions of years. This discovery also highlights the importance of geophysical measurements, like gravity, magnetism, and topography, in uncovering secrets buried beneath the surface. Without the Grail mission, this massive structure would have remained completely hidden, despite its immense size. Below the ancient basin, a silent remnant of cosmic violence lies buried. Whether it's an asteroid's metallic core or a concentration of dense crustal materials, this structure stands as a monument to the immense forces that shaped the moon and the early solar system. Turning to Venus, this planet offers its own set of mysteries, particularly related to its atmosphere. Venus's atmosphere is dense, hot, and primarily composed of carbon dioxide, but it also contains small amounts of oxygen, mostly in its atomic form. What's surprising is that this oxygen is steadily escaping into space, particularly from the upper atmosphere. This ongoing atmospheric loss adds to the enigma of Venus's climate history and raises questions about why the planet is losing oxygen and what it might reveal about its past. The phenomenon was first detected by the European Space Agency's Venus Express mission, which observed ultraviolet emissions that suggested atomic oxygen was escaping from the planet's day side. The escape is especially intense on the planet's night side tail, where interactions with solar wind accelerate the loss. This outflow of oxygen is contributing to Venus's long-term atmospheric change. The oxygen atoms likely come from the breakdown of water and carbon dioxide by ultraviolet radiation, a process known as photodissociation. However, Venus's atmosphere today is nearly devoid of water vapor, which suggests that the oxygen being lost is a remnant from a time when the planet might have had surface water or oceans. The process of oxygen escape involves complex interactions between Venus's atmosphere and the solar wind. Without a strong magnetic field, Venus is vulnerable to direct stripping by the solar wind. Charged particles from the Sun collide with Venus's atmosphere, energizing and ejecting them into space. This mechanism is similar to what happens on Mars, but the denser atmosphere of Venus intensifies the dynamics. Magnetic reconnection events in the induced magnetotail might also play a role in enhancing the energy available for atmospheric loss, contributing to episodic surges of oxygen escape. The gradual loss of oxygen has significant implications for Venus's atmospheric composition. It impacts chemical cycles, particularly sulfur chemistry and haze formation, and offers clues about Venus's past. These escaping oxygen atoms are like a chemical signature of the planet's former state, possibly a time when it had oceans of water and a more temperate climate. Understanding how Venus transitioned from a potentially habitable world to the inhospitable planet we see today is key to unraveling its history. Venus's situation is in stark contrast to Earth's. While Earth's oxygen is replenished through biological processes, Venus's oxygen is a passive trace gas that breaks apart and leaks away into space. This difference emphasizes the role of biology in maintaining an atmosphere and climate. Venus's oxygen escape also provides valuable insight into the study of exoplanet atmospheres. Many exoplanets orbit close to their stars, experiencing intense radiation. By studying Venus, we can better understand how these planets might evolve and how the presence of oxygen doesn't necessarily indicate biological activity. It could simply be a result of atmospheric loss. The escape of oxygen from Venus's atmosphere highlights the planet's transformation and its potential to offer new insights into the evolution of planetary environments. Upcoming missions like NASA's Da Vinci Plus aim to study Venus's upper atmosphere, measuring escaping gases and tracking the processes behind atmospheric loss. These missions will help clarify how Venus's atmosphere evolved, providing crucial data for understanding both Venus and similar exoplanets in our search for life beyond Earth. Mars's lost magnetic field offers a fascinating glimpse into the planet's evolutionary journey. Billions of years ago, Mars was shielded by a global magnetic field much like Earth's. This magnetic shield protected the planet's atmosphere and helped sustain a more habitable environment. However, at some point, Mars's magnetic dynamo shut down, leading to dramatic changes in its atmosphere and climate. Scientists suspect that loss of the field wasn't a gradual process, but rather a sudden and catastrophic event triggered by massive external forces. Evidence gathered from Martian meteorites supports this theory. Isotopic signatures and mineral alignments in these ancient rocks suggest a strong magnetic field early in Mars's history, followed by a complete absence of magnetism in younger rocks. This sharp transition points to a rapid collapse of the dynamo, leaving Mars vulnerable to the solar wind. Once the magnetic field vanished, Mars lost its atmospheric protection. The solar wind, unimpeded, began stripping away lighter gases like hydrogen. Over time, this process eroded the planet's water reserves and thinned its atmosphere, leading to a cooling climate and the eventual disappearance of surface water. As water vanished, habitability on Mars became increasingly unlikely. This sudden loss of the magnetic field marked a critical turning point in Mars's evolution, transforming it from a potentially habitable world to the barren, cold planet we see today. The absence of a global magnetic field is also the reason why Mars's magnetism today is patchy. Unlike Earth, which has a continuous magnetic field, Mars has only localized patches of magnetized crust, remnants of its once active dynamo. These small regional magnetic fields provide limited protection, creating localized magnetospheres but offering no global shield. Mars's dynamo has remained dormant for over 4 billion years, making it a fascinating subject for studying planetary evolution. Understanding why Mars lost its magnetic field could offer valuable insights into how planets evolve, highlighting the importance of core dynamics and heat flow in maintaining atmospheric stability. It also allows us to compare the divergent paths of Earth and Mars, two planets that once shared similar conditions but ended up with dramatically different outcomes. Future missions to Mars might investigate the planet's core more directly. Techniques like drilling into the Martian crust or using seismology to probe the core could reveal whether Mars's core is entirely solidified or still partially molten. Knowing the structure of the core could help determine whether the planet's dynamo could potentially restart, though current observations suggest this is unlikely. The story of Mars's lost magnetic field serves as a cautionary tale about planetary habitability. It shows how even minor shifts in a planet's internal dynamics can drastically alter its potential for life. Mars was once protected, but when its magnetic shield vanished, it entered a geological silence, leaving behind only the traces of a world that might have been. In more recent discoveries, astronomers have begun to detect something truly unprecedented: interstellar objects passing through our solar system. These are not comets or asteroids from within our solar system, but rather cosmic visitors, material ejected from distant star systems. These objects have trajectories, speeds, and compositions that distinguish them from anything previously observed in our own planetary neighborhood. The first confirmed interstellar object, Oumuamua, was discovered in 2017. Its strange hyperbolic orbit, unusual shape, and odd acceleration sparked intense debate. The object was moving too quickly to be bound by the sun's gravity, and its path traced back to no known origin. Unlike a typical comet, Oumuamua had no visible tail, although it did show some non-gravitational acceleration, likely from outgassing. Its exact composition and structure remain a mystery. Some theorized it was a fractured comet, while others suggested it was a nitrogen ice shard, or even a thin, elongated object. The rapid rotation and varying brightness indicated it had a highly elongated shape, but without a tail or visible dust cloud, its true nature remains unknown. Then, in 2019, a second interstellar object was detected, 2I/Borisov. Unlike Oumuamua, this object was clearly a comet, complete with a gas coma and dust tail. However, its chemical composition was different from that of typical solar system comets, confirming that icy bodies are produced in other planetary systems and sometimes get flung into interstellar space. The detection of Borisov confirmed that we can now study material from outside our solar system, which opens up new possibilities for exploring cosmic bodies that were once beyond our reach. These discoveries suggest that interstellar objects are not as rare as once thought. In fact, they pass through our solar system regularly, although their high speeds and faintness make them difficult to detect. With advanced observatories like the Vera Rubin Observatory, astronomers expect to identify more such objects in the future. Each new interstellar object provides a unique opportunity to study material from beyond our own planetary system. These objects could hold valuable clues about the chemical environments of other stars, as their compositions reflect the conditions in the star systems where they originated. For example, the unusually high levels of carbon monoxide detected in Borisov suggest it formed in a colder region than most solar system comets. Similarly, Oumuamua's lack of volatiles points to a different thermal or radiation history. Studying these objects is challenging, though, because of their high velocities. By the time they are detected, they are often already on their way out of the solar system. To intercept them, space agencies would need to rapidly detect and respond, which makes mission planning more complex. Despite the difficulties, space agencies are already considering missions dedicated to studying interstellar objects. One such mission, ESA's Comet Interceptor, is being designed to chase down future interstellar targets. These visitors raise fundamental questions about the ejection of material from planetary systems. How common is it for stars to eject planetary debris into interstellar space? How many fragments of other systems drift through the galaxy, and what might they carry with them? If these objects are widespread, they could even transport organic molecules or the seeds of life, lending some weight to theories like panspermia, though this remains speculative. From a planetary defense perspective, interstellar objects don't pose a significant threat. Their rarity and high speeds make collisions unlikely, but their discovery has opened up an entirely new category of celestial bodies. The detection, tracking, and study of these objects require new methods and tools. Observing these visitors also tests our ability to detect and analyze faint, fast-moving objects, and as our surveys improve, we'll likely find many more of these cosmic travelers. What might seem like a mere speck in the sky could turn out to be a fragment from a system light years away, offering a fleeting but powerful connection to the stars. Each interstellar object that passes through our solar system is a message from a distant corner of the galaxy, a fragment of a planet, an asteroid, or a comet shaped by alien suns, drifting through the vastness of space. When these objects pass through our system, they offer a rare opportunity to study material from far beyond our own planetary neighborhood, connecting us to the broader universe. Comets, often thought of as simple, icy wanderers, continue to surprise us with their behaviors. One of the most intriguing mysteries revolves around their deceleration patterns. Do short-period comets decelerate differently than long-period ones? Could their deceleration be influenced by the size of their nuclei, their composition, or even the tilt of their orbits? While current data is still limited, larger and more detailed studies could provide the answers. Future missions, possibly with landers or penetrators, might allow us to study the interiors of comets, giving us a deeper understanding of their mechanical and thermal properties. These insights could help us refine the models that explain the forces shaping their paths. Until then, each unexplained deceleration in a comet's motion only adds to the mystery of their behavior. Io, one of Jupiter's moons, is the most volcanically active body in our solar system. Its surface is continuously reshaped by eruptions, lava flows, and sulfur-rich plains. Among these features are lava lakes, persistent pools of molten rock that have been active for decades. Unlike terrestrial lava lakes, which often cool and crust over quickly, Io's lava lakes are constantly replenished with heat, keeping them alive and active over long periods. One of the most well-known lava lakes on Io is Loki Patera, a massive lava-filled depression over 200 kilometers wide. This lake exhibits a distinctive cycle, brightening and dimming as the surface crust sinks and reforms. It's like a giant cauldron slowly bubbling away, with activity that dates back at least to the 1980s, if not further. Infrared and thermal imaging from spacecraft like Galileo as well as ground-based telescopes have allowed scientists to track the fluctuations in Loki Patera's brightness. These changes in brightness correlate with temperature shifts, suggesting that the lake undergoes resurfacing events. The energy driving this activity is immense, indicating that the heat source within Io is not only powerful but persistent. Tidal heating, driven by Io's gravitational interactions with Europa and Ganymede, is the primary source of this energy. As Io orbits Jupiter, it is stretched and compressed by the gravitational forces of its neighboring moons, generating internal friction and heating the moon from the inside. This heat rises to the surface, fueling ongoing volcanic eruptions and the persistence of Io's lava lakes. It's a geological process, unlike anything on Earth. Other lava lakes on Io, such as Play and Tupon Patera, also exhibit long-term activity. These lakes go through complex resurfacing cycles, with crustal rafting and intermittent eruptions. Unlike Earth's volcanoes, Io's volcanic activity is driven almost entirely by tidal forces, not mantle convection. This unique mechanism challenges our models of crust stability and magma replenishment. The lava lakes themselves are not passive. They actively overturn, with fresh lava rising to the surface and solidified crust sinking back into the lake. These cycles can range from regular to chaotic, and the exact mechanisms behind them are still under investigation. The composition of Io's lava is also extraordinary. It may consist of ultramafic silicates, which are hotter and more fluid than most terrestrial lavas. Some models suggest temperatures exceeding 1,600 degrees Celsius, making them some of the hottest lavas known. The thin atmosphere on Io, primarily composed of sulfur dioxide, is continuously replenished by volcanic activity. As lava lakes erupt, they release vast amounts of gas and dust which either escape into space or freeze back onto the surface. These emissions contribute to the plasma environment around Jupiter, forming the Io plasma torus. Studying Io's lava lakes provides valuable insight into volcanic processes in extreme environments. It also serves as a natural laboratory for understanding tidal heating, a process relevant to icy moons like Europa and Enceladus. Though on Io this heating takes the form of fire instead of water, the underlying principles are shared across a range of worlds. The volcanic system on Io is dynamic and continuously evolving. Eruptions may block or reconnect lava lakes, alter the thickness of the crust, or change drainage patterns. Tracking these changes requires long-term monitoring, which could be achieved using infrared observatories or future missions, such as the proposed Io Volcano Observer. Despite Io's distance from Earth, it provides a glimpse into how diverse and dynamic planetary surfaces can be. Its lava lakes persist not by chance, but due to an ongoing tidal interaction with Jupiter and its moons. These lakes have been active for decades, and may continue for centuries to come. In the cold reaches of the outer solar system, Io burns brightly, a world of enduring fire fueled by gravity and time. The Sun, much like the planets in our solar system, exhibits its own unique rotational behavior. Unlike solid planets, the Sun is a sphere of hot plasma, and as such, it experiences differential rotation. This means different parts of the Sun rotate at different speeds. At the equator, the Sun takes about 24 to 25 days to complete one rotation, while near the poles, it takes around 35 days. This variation in rotation speed is due to the complex interactions between the Sun's plasma and its magnetic fields. The outer convective zone of the Sun transports energy through rising and falling currents of gas, and these currents interact with the Sun's internal structure, causing the equator to spin faster than the poles. This differential rotation plays a crucial role in the Sun's magnetic cycle. The differing speeds of rotation stretch and twist magnetic field lines across the Sun's surface. Over time, this leads to magnetic buildup and release, resulting in phenomena like sunspots, solar flares, and coronal mass ejections. These events follow an 11-year cycle, which is directly tied to the Sun's rotation and the redistribution of its magnetic energy. The twisting of magnetic fields also drives the solar dynamo, the engine responsible for generating the Sun's magnetic field. At certain latitudes, these magnetic loops become so distorted that they emerge as sunspots visible on the Sun's surface. Helioseismology, the study of wave propagation within the Sun, has provided more detailed insight into the Sun's rotation. By observing sound waves moving through the Sun, researchers have been able to map its internal rotation. These studies have revealed not only surface rotation, but also shear layers deep inside the Sun, where the rotation rates shift dramatically. One such key region is the tachocline, the transition zone between the Sun's radiative and convective zones. Here, rotation changes rapidly with depth, playing a critical role in the Sun's magnetic field generation. The Sun's rotation is also linked to space weather. The distribution of sunspots and solar flares depends on how the Sun rotates. During periods of high activity, the faster-moving equator tends to face Earth more frequently, increasing the likelihood of geomagnetic storms. These storms can disrupt satellites, power grids, and communication systems on Earth. The study of the Sun's rotational dynamics also informs our understanding of stellar evolution. Younger stars tend to rotate faster and more uniformly, but as stars age, magnetic braking slows their spin and increases differential rotation. By studying the Sun, we gain insights into how stars evolve and how their rotation affects their magnetic activity. Understanding the Sun's differential rotation not only helps us learn more about our own star but also provides valuable context for exoplanet research. The rotation of a star influences its magnetic activity, which in turn affects the habitability of planets in its system. By decoding the rotation patterns of our own Sun, scientists can apply these findings to other stars, improving our understanding of how stellar dynamics shape planetary environments. Jupiter's influence on Earth extends far beyond its size. While it occasionally nudges comets toward Earth, its gravitational pull more often acts as a shield, protecting the planet from potential cosmic impacts. This role, while subtle, plays a significant part in the long-term stability of Earth's biosphere, contributing to the gradual development of biodiversity. Recent studies suggest that Jupiter's gravitational force may also affect shorter-term climate cycles that span from 60,000 to 400,000 years. These cycles, linked to variations in Earth's orbit, could influence the timing and intensity of ice ages. While these changes are subtle, evidence of them can be found in ice core samples and sediment layers, offering a glimpse into Jupiter's role in shaping Earth's climate over millennia. Jupiter's gravity doesn't just affect Earth's orbit, it also influences the precession of Earth's equinoxes. This precession alters the tilt of Earth's axis over time, which, when combined with changes in Earth's orbital shape, affects the seasonal contrasts and climate patterns. These gradual shifts are likely responsible for the rhythmic patterns of glacial cycles, synchronized with the alignment of the planets. By studying Jupiter's gravitational impact, scientists can refine their climate models, offering clearer insights into past climate variations and better predictions for the future. This knowledge is crucial for distinguishing between natural climate cycles and human-induced climate change, helping us better understand Earth's long-term climate behavior. When comparing Earth's climate stability to that of Mars, it becomes clear how significant Jupiter's influence is. Mars, lacking a large stabilizing neighbor like Jupiter, experiences more extreme and unpredictable variations in its axial tilt. Earth's relatively stable orbit, influenced by Jupiter, has played a key role in maintaining the planet's habitability. Without Jupiter's stabilizing effect, Earth's climate might have been far more chaotic. The arrangement of our planetary system, with Jupiter at its heart, has made Earth's climate more predictable and conducive to life. Jupiter's gravitational influence shapes Earth's climate, stabilizes its orbit, and shields it from hazardous space debris, playing an essential role in the conditions that support life here. On Mars, despite the absence of a global magnetic field, auroras still occur. Auroras are typically associated with planets that have strong magnetic fields like Earth, where charged particles from the Sun are funneled toward the poles along magnetic field lines. But Mars presents a unique case. Although it lacks a global magnetic field, Mars still experiences auroras. These faint fleeting lights are visible not only near the poles but across various latitudes, even on the night side of the planet. These Martian auroras are generated by solar wind interactions with localized magnetic fields found in the crust. These magnetic remnants left over from Mars's ancient magnetic field still influence the planet's upper atmosphere. The MAVEN mission has confirmed the existence of these auroras, using ultraviolet imaging to detect the light emissions. Unlike Earth's auroras, which glow in visible light, mostly green and red, Martian auroras are observed in ultraviolet wavelengths, making them invisible to the naked eye. These auroras vary in intensity and distribution, often influenced by solar storms, particularly coronal mass ejections. During such storms, the flow of energetic particles increases, enhancing the auroral activity. However, because the magnetic fields on Mars are patchy and non-uniform, the auroras are irregular and transient, unlike the more consistent displays on Earth. Mars's lack of a protective magnetic shield leaves its atmosphere vulnerable to solar wind erosion. As solar particles collide with Mars's atmosphere, they gradually strip away lighter elements, including hydrogen. In this sense, the auroras on Mars are not just beautiful displays. They are a visible manifestation of the ongoing atmospheric loss caused by solar radiation. This discovery challenges traditional ideas about planetary auroras. It shows that even without a global magnetic field, localized magnetism can still produce auroral emissions. This phenomenon has important implications for other rocky planets, including exoplanets with weak or patchy magnetic fields, providing a new perspective on atmospheric interactions in space. By studying Martian auroras, scientists gain valuable insights into atmospheric escape processes. By tracking the location and timing of auroral events, researchers can understand how solar energy is deposited into Mars's upper atmosphere. These energy transfers play a key role in ionization, heating, and chemical reactions at high altitudes. The distribution of auroras can also shed light on Mars's subsurface magnetic properties. Mapping these emissions helps scientists refine their models of Mars's magnetic crust, complementing data gathered from orbital magnetic surveys and enhancing our understanding of the planet's internal history. 3 distinct types of auroras have been observed on Mars: discrete, proton, and diffuse. Discrete auroras are aligned with the planet's crustal magnetic fields, while proton auroras form when solar wind protons collide with hydrogen in Mars's upper atmosphere. Diffuse auroras, which occur more widely and erratically, are typically linked to solar storms and are more chaotic in nature. These auroras are closely tied to Mars's current space weather environment. Unlike Earth, where the magnetosphere provides a stable shield, Mars interacts directly with the solar wind, creating a more dynamic and sometimes hazardous atmospheric interface. The existence of auroras on an unmagnetized planet offers a fascinating challenge to our understanding of planetary atmospheres. Mars's auroras are a testament to the importance of localized magnetic interactions, and they highlight the lasting impact of a once active dynamo. The Martian auroras also serve as a reminder of the planet's turbulent past, a planet that may have once had a more Earth-like environment, with a strong magnetic field protecting its atmosphere. On the surface of Mars, another mystery unfolds: the movement of its sand dunes. Despite Mars's thin atmosphere, its dunes migrate slowly but steadily across the planet's surface. Even more perplexing is that some dunes shift in regions where wind activity is minimal or undetectable. This suggests that Martian dunes are influenced by factors other than wind, which are still not fully understood. NASA's Mars Reconnaissance Orbiter has captured images of these dunes over many years. By comparing these images, scientists have observed movement in dune fields, with some shifting several meters per Martian year. These shifts occur even in areas with calm atmospheric conditions, sparking curiosity about the forces driving this movement. One possibility is that occasional gusts of wind, though infrequent, are strong enough to move the sand during brief, intense events. Mars also experiences sudden pressure changes that can create local wind bursts capable of mobilizing sand. These gusts are hard to predict and often go unnoticed in weather models, but they may explain sporadic dune movement. Thermal winds could also play a role. As temperatures on the Martian surface fluctuate dramatically between day and night, convection currents could form, creating weak but persistent airflows capable of moving fine particles. Though the effect is subtle, it could accumulate over time and account for the slow, steady migration of dunes. Dust devils, which frequently occur on Mars, may also contribute to dune movement. These small, localized vortices have been known to clean solar panels and stir surface dust. They might also disturb sand layers, setting off chain reactions that cause sand grains to shift. Another possibility is that some dune movement is driven by sublimation. In Mars's polar regions, carbon dioxide frost forms seasonally. As this frost sublimates in spring, it releases gas beneath the ice which could destabilize the surface and trigger dune movement. This gas-driven flow could be strong enough to dislodge sand grains and set dunes in motion, even in the absence of wind. Over time, the movement of these dunes becomes more significant, suggesting that Mars's surface is still evolving, albeit slowly. This shifts our understanding of Mars from a static, frozen desert to a dynamic world with ongoing geological processes. Understanding how Martian dunes move is crucial for planning future missions. Rovers and landers must take into account the possibility of loose, shifting surfaces. By mapping active dunes, scientists can better predict where to land and how to navigate safely across Mars's surface. Additionally, the movement of dunes could offer clues about Mars's past climate. If dunes move more rapidly in the past, it could suggest that Mars once had stronger winds or a thicker atmosphere. Studying these dunes helps us understand not just Mars's surface dynamics, but also the history of its climate and atmosphere. The mystery surrounding systems with multiple moons or distant, stable orbits continues to puzzle scientists. The amount of energy and angular momentum involved often seems inconsistent with what is known about impact dynamics. Yet, there are several hypotheses that might explain these intriguing cosmic phenomena. One such possibility is rotational fission. As an asteroid spins faster, often due to the Yorp effect, which is a torque generated by solar radiation, it can shed material. This material might form a secondary body that eventually becomes gravitationally bound. This process has been observed in asteroids close to the Sun and could explain the formation of many binary asteroid systems. However, this theory has limitations. The moons created by this process tend to be tightly bound to the asteroid, not orbiting at the larger distances seen in some binary systems. Additionally, this mechanism assumes that the parent asteroid is a loose pile of rubble, which isn't always the case. In fact, every binary system requires its own modeling. Another hypothesis, gravitational capture, might explain the origin of some of these moons. In the early days of the solar system, chaotic and dense environments could have caused small objects to lose energy and become trapped by larger ones. However, such captures are rare today and usually unstable. For a satellite to remain in orbit around an asteroid, additional mechanisms would be required to dampen its orbit and stabilize it. Asteroid moons can also form through tidal disruption during planetary flybys. When an asteroid passes too close to a planet, the planet's gravity can stretch and fragment the asteroid. Some of the debris might stay bound to the original asteroid. This process, however, is complex and depends on several factors, including orbital geometry and the asteroid's cohesion. Moons significantly impact the behavior of their parent asteroid. The mutual tidal forces between the asteroid and its moon can cause changes in their spin states. Over time, these interactions may synchronize or destabilize their rotations. In some cases, systems can even experience mutual eclipses or occultations, giving scientists a valuable opportunity to study the dynamics of these bodies in greater detail. Tracking asteroid moons can also provide critical information about the parent asteroid's mass and density. By observing the moon's orbit, Scientists can infer the primary body's gravitational field and from there estimate its mass. Combining this with size measurements, they can calculate the bulk density, which gives insights into the asteroid's internal composition. Many binary systems reveal that their primary asteroids are less dense than solid rock, indicating that they may have porous interiors. Asteroid moons play a significant role in planetary defense strategies. A deflection mission aimed at an asteroid with a binary system needs to account for both bodies. The recent DART mission demonstrated this concept by impacting the moon of the asteroid Didymos. The results showed how the presence of a satellite can influence the outcome of kinetic deflection events. As telescope surveys continue to improve, more asteroid moons are being discovered. Some asteroids even have multiple moons, revealing the complexity of these small body systems. These systems defy simple classifications and showcase the diverse ways that objects in the solar system evolve and interact. The study of asteroid moons not only helps us understand the dynamic nature of the solar system, but it also highlights the incredible variety of interactions and pairings that can occur in the vastness of space. But moons don't always stay bound to their planets. Over time, some natural satellites can escape their gravitational bonds. Moons are typically thought of as permanent companions to their planets, held in stable orbits by gravity. Yet in certain circumstances, moons can drift away or even escape entirely. This slow orbital evolution is influenced by tidal interactions, resonances, and long-term gravitational effects. For example, Earth's moon is gradually receding from our planet at a rate of approximately 3.8 centimeters per year due to tidal interactions. The Earth's rotation drags ocean bulges ahead of the moon, transferring energy and gradually pushing it outward. Over billions of years, this process could eventually result in the moon reaching a point where it is no longer gravitationally bound to Earth. However, this would take an immense amount of time. Other moons, like Mars's moon Phobos, are on the opposite trajectory. Phobos is spiraling inward, and tidal forces are causing it to lose altitude. It is predicted that Phobos will either crash into Mars or break apart into a ring system within the next 30 to 50 million years. This highlights the fact that not all moons are destined to escape. Some are doomed to fall into their parent planet. For gas giants, tidal interactions are even more complex. Some moons migrate outward, while others become locked in orbital resonances. These resonances can amplify orbital eccentricities, or even lead to orbital swaps. In extreme cases, instability could cause moons to escape or be captured into different configurations. Saturn's moon Hyperion is a prime example. Its chaotic rotation, influenced by Titan's gravity, could eventually cause dramatic changes in its orbit. While its orbit is stable for now, small gravitational perturbations over time could lead to significant shifts. Moons that pass too close to their planet's Roche limit, the region where tidal forces become strong enough to break apart objects, are at risk of disintegration. Others may be flung outward as a result of planetary migration. In the early solar system, the shifting of planets likely led to the loss of many moons. Some moons were ejected into solar orbit, becoming asteroids or even dwarf planets. Others may have collided with their parent bodies or nearby moons. Captured moons are particularly vulnerable because they often have eccentric or inclined orbits. Without stabilizing forces, these orbits can decay over time. For example, Neptune's largest moon, Triton, is believed to be a captured object. Its orbit is gradually decaying, and tidal forces may eventually cause it to break apart or be destroyed. While moons can escape their planets, they can also transition into different states, or a moon that gains energy through resonant interactions or gravitational assists could migrate outward and eventually stabilize in a distant orbit. In some rare cases, it might even become a minor planet. These transitions are unusual but possible, especially in systems with multiple moons or nearby massive bodies. Simulations of long-term planetary dynamics show that satellite systems are not fixed. Over billions of years, orbital interactions can reshape them. This dynamic behavior affects our models of planet formation and satellite evolution. Moons evolve along with their planets, and understanding these processes has significant practical implications. For example, artificial satellites orbiting Earth are subject to similar dynamics. albeit on much shorter timescales. The study of moon escape mechanisms helps inform mission planning and orbital mechanics. Moreover, escaping moons present interesting philosophical questions. What happens when a body once bound to a planet is set free? In cosmic terms, these are stories of change, not loss. The solar system is a dynamic arena, where even the most stable orbits can eventually come undone. Moons may be companions for a time, but they are not eternal. Over time, tides and gravity will shape their paths, sometimes drawing them in, and other times sending them off into the vast dark expanse of space. Magnetic fields might play a more significant role than we think. Neptune, for example, has a magnetic field that's both tilted and offset, which is unlike anything we've seen elsewhere in the solar system. While this field doesn't directly influence the planet's wind generation, it could interact with charged particles and create subtle atmospheric effects. Scientists are still investigating how Neptune's magnetism, its rotation, and the movement of deep fluids inside the planet work together. Studying Neptune's winds is more than just an intriguing puzzle. It helps inform models for exoplanet atmospheres, especially for gas giants that orbit far from their stars. These models need to consider the internal heat of a planet and the non-solar mechanisms that contribute to energy transfer, which we can learn directly from Neptune's behavior. Looking ahead, future missions to Neptune may finally provide the answers we need. Proposed orbiters and atmospheric probes aim to study the planet's internal structure, heat flow, and weather systems directly. Until then, the violent winds that howl across Neptune's surface remain one of the most mysterious features in our solar system. Meanwhile, far closer to the Sun, Mercury tells its own story. It has no traditional atmosphere, thanks to its weak gravity and close proximity to solar radiation. Instead, Mercury boasts an exosphere, a very thin cloud of atoms that surrounds the planet. This exosphere is in constant flux, replenished and stripped away by impacts, radiation, and solar wind. Unlike Earth's atmosphere, Mercury's exosphere is not held tightly by gravity. Atoms within it often escape the planet completely. Its composition is primarily made up of oxygen, sodium, potassium, calcium, and hydrogen, elements that are ejected from Mercury's surface and then drift freely in space. One of the key factors contributing to the exosphere is micrometeoroid bombardment. Due to Mercury's close orbit to the Sun, the planet is constantly bombarded by interplanetary dust. When these micrometeorites strike the surface, they vaporize small amounts of material, which are then ejected into the exosphere. This process, known as impact vaporization, happens continuously, keeping the exosphere in a steady state. Solar radiation also plays a significant role, with ultraviolet light and extreme solar heat causing a process called photon-stimulated desorption. Photons knock atoms loose from the surface, particularly sodium and potassium. These atoms then glow faintly in the sunlight, making Mercury's exosphere visible from Earth-based telescopes. Additionally, solar wind sputtering, the collision of charged particles from the Sun with Mercury's surface, further contributes to the exosphere. This process adds more hydrogen and helium to the mix. As a result, Mercury's exosphere is a mixture of material from the planet's surface and particles originating from the Sun, constantly changing with space weather conditions. Despite its thinness, Mercury's exosphere can form a detectable tail. Sodium atoms are pushed by solar radiation into a long comet-like stream extending millions of kilometers into space. Although this tail is invisible to the naked eye, sensitive instruments can detect it. This dynamic structure is heavily influenced by the Sun's activity and Mercury's orbital position. The MESG spacecraft provided the first comprehensive study of Mercury's exosphere, revealing that its composition varies depending on the time of day, latitude, and solar events. For instance, calcium is more abundant at dawn, likely due to thermal desorption. These patterns give scientists valuable clues about the composition of Mercury's surface and the energy that's impacting the planet. Mercury's weak magnetic field also affects the exosphere's dynamics. It deflects some of the solar wind and funnels charged particles towards specific areas of the planet. This interaction can enhance the ejection of atoms in certain regions, adding another layer of complexity to Mercury's exospheric behavior. It's a delicate balance of shielding and exposure, with the exosphere constantly in flux. Studying Mercury's exosphere isn't just about understanding an airless world, it provides valuable insights into planetary geology. By analyzing the exosphere's composition, scientists can infer the types of elements present in Mercury's crust. For example, the presence of sodium and potassium suggests that volatile elements have survived, despite the intense solar heating Mercury faces. This challenges earlier models that assumed Mercury's formation involved the loss of these volatile materials. Mercury's exosphere is constantly renewing itself, never reaching a state of equilibrium. It shifts and evolves in response to solar activity, impacts, and planetary rotation. This constant instability makes it difficult to model, but also offers rich data on how surface and atmospheric interactions occur in extreme environments. Mercury's exosphere may not be an atmosphere in the traditional sense, but it's a dynamic and ever-changing veil around the planet, shaped by light, heat, and collisions. As we move further into the solar system, Venus presents another fascinating mystery. Venus, so similar to Earth in many ways, lacks a significant magnetosphere, and scientists are still puzzled by why that is. Both Venus and Earth likely formed under similar conditions, so Venus's lack of a magnetic field is unexpected. For a planet to have a magnetosphere, it needs a conducting liquid core, rapid rotation, and convection, features Venus should theoretically possess. Yet, Venus remains silent in terms of magnetism, a puzzle that continues to baffle planetary scientists. On Earth, the magnetic field is generated by a dynamo. The motion of liquid iron in the outer core creates the magnetic field. Venus is believed to have a similar core, molten and metallic, but it's unclear why it doesn't produce a dynamo. Some theories suggest that Venus's slow rotation may not generate the shear or turbulence needed to create a dynamo, but other models argue that even a slow-spinning planet could sustain a magnetic field under the right conditions. Another possibility is that Venus's core could have stratification, thermal or compositional layers that prevent convection. If this layering is present, it could inhibit the mixing required to sustain a dynamo. However, this idea remains difficult to test, as we lack direct measurements of Venus's interior. Alternatively, Venus may have once had a magnetic field that later died out. If its core cooled or solidified differently from Earth's, the dynamo could have shut down. Venus's resurfacing activity, which has erased much of the planet's ancient surface, makes it hard to find any magnetic fossils that could reveal clues about Venus's past. The lack of a magnetosphere on Venus has important implications for its atmosphere. Without a protective magnetic shield, the solar wind directly interacts with Venus's upper atmosphere, stripping away particles over time. Despite this, Venus retains a dense, carbon dioxide-rich atmosphere, suggesting that any atmospheric loss is slow and may be balanced by volcanic replenishment. While Venus lacks a magnetosphere, it does have an induced magnetic field. Solar wind interaction with Venus's ionosphere generates weak magnetic fields, but these are temporary and offer little protection from radiation and particle loss. However, they contribute to the complex plasma environments that missions like ESA's Venus Express have observed. Understanding Venus's magnetic silence can help refine theories about planetary dynamo processes. Venus challenges our assumptions about magnetic field generation in terrestrial planets and raises important questions about exoplanet habitability. Magnetic fields can protect a planet's atmosphere, which is vital for long-term climate stability. Venus demonstrates that not all Earth-like planets have magnetic fields, and their histories may diverge in unexpected ways. Finally, Pluto's orbit provides yet another fascinating example of cosmic mechanics. Despite sharing an orbit that brings it close to Neptune, Pluto never collides with the gas giant. This is because Pluto and Neptune are locked in a 3-2 orbital resonance, meaning that for every 3 orbits Neptune completes, Pluto completes exactly 2. This resonance keeps their orbits stable and prevents close approaches. This orbital relationship is the result of precise gravitational mechanics, finely tuned over millions of years. When Pluto reaches its closest point to the Sun, called perihelion, Neptune is always positioned far away. Their orbits are arranged in such a way that even though they share overlapping paths, their motions never bring them close enough for a collision. Pluto's orbital inclination also plays a significant role in this stability. The planet's orbit is tilted by 17 degrees relative to the solar plane, which helps prevent any potential collisions with Neptune. Even if both planets are at the same point in their elliptical orbits, Pluto is likely to be above or below Neptune's orbital plane. This orbital resonance is further evidence of Neptune's past migration. The current distribution of Pluto's moons and other objects in the Kuiper belt supports models suggesting that the early solar system was highly dynamic, with planets shifting positions and reshaping the paths of minor bodies. Pluto's status as a dwarf planet doesn't reduce the importance of this orbital resonance. In fact, the precision of Pluto's orbit highlights the dynamical structure of the Kuiper belt and demonstrates how gravity can organize seemingly chaotic systems into stable configurations. Even after billions of years, this resonance ensures Pluto's orbit remains remarkably resilient, even in the face of gravitational forces from other bodies. The Pluto-Neptune resonance is a fascinating example of how gravitational forces can maintain order in complex, multi-body systems. This unique relationship offers valuable insights into how similar arrangements might exist in exoplanetary systems. As we continue to explore the Kuiper belt, we may uncover more such resonant interactions, shedding light on the history of planetary migration, ancient collisions, and possibly even undiscovered objects. Pluto and Neptune's synchronized motion could be just one example of a grand cosmic symphony, a rhythm maintained solely by gravity, echoing the deep past of the solar system. In the far reaches of space, this silent dance continues, preserved by forces older than time itself. Turning to the Sun, we find a dynamic rhythm of its own, the 11-year solar cycle. This cycle involves the complete reversal of the Sun's magnetic field, a process that flips its north and south poles. The event signals the peak of the solar cycle, a period marked by increased solar activity, including sunspots, solar flares, and massive coronal mass ejections. This dramatic change in the Sun's magnetic field is the result of plasma flows deep inside the Sun. The Sun's convection currents and differential rotation twist and stretch the magnetic field lines, causing them to become so tangled that they eventually reorganize, reversing the Sun's magnetic polarity. This flip triggers a series of changes, affecting not just the Sun itself, but the entire heliosphere, the vast bubble of space that surrounds our solar system. As the magnetic field reorganizes, sunspot numbers rise, solar winds intensify, and space weather becomes more extreme. These changes are significant, not only for scientists studying the Sun, but also for those concerned with the practical impact on Earth's technology and infrastructure. During this heightened solar activity, geomagnetic storms can affect satellites, communication systems, and even power grids. Understanding the solar cycle is essential for predicting these events and minimizing their effects. The reversal of the Sun's magnetic field also reshapes the heliosphere, influencing how cosmic rays and solar particles flow through space. These shifts alter the radiation environment for spacecraft and planetary atmospheres, making the solar cycle a powerful force in the space weather system. The cycle itself isn't a new discovery. Scientists have tracked it for centuries through sunspot records, and more recently with the help of satellites. Tools like the Solar and Heliospheric Observatory (SOHO) and the Solar Dynamics Observatory (SDO) provide real-time data on the Sun's magnetic strength, polarity, and solar emissions, giving us a clearer understanding of the cycle's regularity. Though the solar cycle is predictable, the exact timing and intensity of each cycle are still challenging to model. The Sun's deep dynamo mechanism remains largely hidden from view, and the complex behavior of turbulent plasma inside the Sun defies easy explanation. Despite decades of study, accurately forecasting the amplitude and precise timing of each cycle remains a challenge. Additionally, the reversal isn't always perfectly symmetrical. Sometimes the northern pole flips before the southern, creating a lag between the two hemispheres. This asymmetry adds another layer of complexity to our understanding of the Sun's behavior. The Sun's magnetic cycle provides an excellent model for understanding the magnetism of other stars. Many Sun-like stars exhibit similar cycles, though their periods and intensities can differ. By studying the Sun, we gain valuable insights into stellar magnetism and its role in habitability, climate, and the dynamics of planetary systems. The Sun's 11-year cycle connects internal processes to space weather, illustrating how magnetic fields evolve in fluid stars and how those changes reverberate across vast distances. Every 11 years, the Sun's magnetic field shifts, altering the direction of energy and reshaping the space surrounding us. Now, back in the asteroid belt, a peculiar feature catches our attention: unexplained empty zones, or Kirkwood gaps, that exist between Mars and Jupiter. These gaps, first identified in the 19th century, are regions in the asteroid belt where few or no asteroids are found. They are located at specific distances from the Sun, corresponding to orbital resonances with Jupiter. In most cases, the gaps are the result of gravitational interactions with Jupiter, which cause asteroids to become destabilized over time, increasing their eccentricity and pushing them out of the gap. This mechanism shapes the overall structure of the asteroid belt. However, some of the gaps defy easy explanation. Some are surprisingly wide, while others occur in areas where Jupiter's influence is weaker. These anomalies suggest that other forces could be at play. For example, the Yarkovsky effect, a small thermal force caused by the rotation of asteroids, can gradually shift their orbits over millions of years. This process may cause asteroids to move into resonant zones where they are eventually ejected, contributing to the maintenance of the Kirkwood gaps. Yet, this effect doesn't fully explain the sharpness or formation of some of these voids. Another theory points to early instability in the solar system. During a period known as the giant planet migration, Jupiter and Saturn may have moved rapidly in their orbits, sweeping through the asteroid belt and scattering or clearing vast regions. This chaotic period could have left behind fossilized gaps, zones that were created during this time of planetary upheaval. Data from spacecraft like Dawn, which explored Vesta and Ceres, supports this idea. The asteroid belt contains a diverse range of compositions and collisional histories, further complicating our understanding of its structure. Some models also suggest that hidden resonances with planets like Saturn or Uranus could play a role in shaping the belt. While these planets are farther from the Sun, their gravitational influence may still be strong enough to create weaker but still significant perturbations in the orbits of asteroids. The combined influence of multiple planets over long periods could explain some of the gaps that are not easily attributed to Jupiter alone. Adding to the mystery, there are gaps in the asteroid belt that appear asymmetric, more pronounced on one side of a resonance. This asymmetry may reflect past differences in asteroid populations or the way they have evolved through collisions. These complex patterns suggest that the asteroid belt's evolution is more intricate than previously thought, involving not just gravitational resonance, but also the transfer of angular momentum and the influence of planetary migrations. Even within these gaps, asteroids are not completely absent. Occasionally, asteroids are found within the gaps, often on unstable orbits. These transient objects may have recently entered the gap or survived after being ejected from resonant zones. Their presence offers a unique insight into the ongoing dynamics of the asteroid belt. In a broader sense, the gaps in the asteroid belt provide a snapshot of the early solar system. They are fossil records of planetary migration, collisions, and resonant interactions, preserving the hidden history of how our solar system was shaped over billions of years. Even the emptiness within these gaps carries structure, revealing the deep gravitational battles that have sculpted the asteroid belt. Turning to the fascinating world of exoplanets, some distant worlds may experience molten iron rain. These hot Jupiters and lava planets, which orbit incredibly close to their stars, endure temperatures that can exceed 2,000 degrees Celsius. Under such extreme conditions, rock and metal vaporize in the upper atmosphere. As the planet rotates and the temperature drops on the night side, these vapors condense and fall as molten iron rain. WASP-76b, one such planet, has been observed with high-resolution spectroscopy. This data reveals the presence of iron vapor in its atmosphere, which forms on the day side and condenses into iron rain on the night side. This process is an extreme example of how intense heat gradients and rapid atmospheric circulation can create such bizarre weather systems. Winds on this planet may exceed 5,000 kilometers per hour, moving material between the planet's hot and cold hemispheres. These findings are not just theoretical. Chemical models and infrared spectra provide strong evidence for the condensation of metals at high altitudes. It's a world where clouds of metal rain down from the sky, and vaporized rock creates a landscape unlike anything we can imagine. The exoplanets we're discovering are increasingly diverse, with environments and weather systems far beyond the limits of our solar system's familiar planets. Our solar system's earliest stages were far from peaceful. The process of planetary formation was violent, with planetary surfaces, including Earth's, partially molten during the magma ocean phase. This molten state likely led to the evaporation and recondensation of silicates and metals, which could have formed metallic clouds and even caused localized rain of molten metal. The impact believed to have formed the Moon likely vaporized large parts of Earth's mantle. This vaporized material may have condensed into droplets, raining back down as iron-rich material, possibly explaining the unusual distribution of iron in Earth's crust and mantle. Mercury, with its high iron content, may have experienced a similar process. Its thin mantle and large core suggest it lost lighter materials early in its formation. A vaporization and condensation scenario could explain Mercury's unique composition, suggesting that molten metal rain may not just be an exotic feature of exoplanets. It could reflect events in our own past. These findings blur the lines between planetary weather and geology. On molten worlds, clouds are made of vaporized rock, and the rain consists of metals. This challenges our understanding of atmospheric models, which must now integrate fluid dynamics, chemistry, and extreme thermodynamics to account for such environments. Exoplanet observations are refining our understanding of planetary diversity. Not all planets follow Earth's path. Some are shaped by their proximity to their stars, gravitational locking, and volatile migrations. Studying the weather on these worlds offers clues about their evolution and how they might transition to more stable states. Metallic rain has a profound effect on surface composition. On exoplanets, repeated condensation and precipitation could lead to the stratification of surface materials, which may affect the planet's reflectivity, erosion, and long-term habitability, if these extremes eventually stabilize. On a molten world, even the rainfall could sculpt the land. These metallic rains are detected through indirect methods. Instruments track changes in absorption lines as atoms and molecules move in the atmosphere. Upcoming telescopes, such as the James Webb Space Telescope, will have the sensitivity to confirm the presence of these exotic weather phenomena. We might even discover other types of rain, like silicate or glass corundum rain. The concept of molten rain challenges our instincts. We typically associate rain with water and life, but on these worlds, rain is a destructive force, a storm of molten metal falling from a fiery sky. Yet this process, though alien, could be linked to the early dynamics of Earth-like planets. There was a time when our skies, too, may have held clouds of steam and metal, and storms rained molten iron. These early planetary dynamics are still written in the crusts of worlds, both here and beyond. On Mars, dark lines appear and disappear with the seasons, creating another mystery. Mars hosts recurring slope-line RSL, narrow, dark streaks that form seasonally on steep slopes. These features appear during the warmer months and fade during colder temperatures, often reappearing in the same locations year after year. Identified first in 2011, RSLs have sparked debate about the possibility of liquid water on present-day Mars. While their behavior remains unexplained, RSLs typically form on sun-facing slopes, measuring a few meters in width and stretching hundreds of meters long. They appear darker than the surrounding terrain, suggesting they may be the result of moistening or disturbances in the soil. Initially, scientists thought these dark streaks were caused by briny water. Mars is too cold for liquid water to exist in pure form, but salts can lower the freezing point, allowing brine to flow. This could mean that briny seeps, perhaps from underground aquifers or atmospheric absorption, were responsible for these flows. However, further data complicated this theory. Spectral analysis did not confirm the presence of water in most cases, and some RSLs appear in conditions too cold or dry for known water activity. This has led to alternative hypotheses, such as dry granular flows, small landslides triggered by CO2 sublimation, or thermal stresses. The role of hydration in these events remains up for debate, as it's challenging to distinguish between brine activity and dry avalanches with current remote sensing technology. Local soil chemistry variations might also play a role in the formation of RSLs. The Mars Reconnaissance Orbiter, MRO, continues to monitor RSLs at different sites, and its high-resolution camera captures changes in their width and shape over time. The recurring nature of these streaks suggests a repeating environmental trigger, but the variability by region and slope angle makes a unified explanation elusive. One possibility is that CO2 frost processes, which occur during seasonal temperature changes, could destabilize the slope material. This would explain the timing and movement of some RSLs without invoking liquid water. Similar processes occur on Earth with dry ice on sand, and the CO2 sublimation model fits certain cases. However, some RSLs appear in equatorial regions where CO2 frost is unlikely, adding to the complexity. The mystery of RSLs is important for more than just geology. If liquid water is involved, even temporarily, these regions could become prime targets for astrobiological research. They would also fall under planetary protection protocols, which restrict human exploration to avoid contamination. Whether wet or dry, RSLs offer a glimpse into Mars's dynamic geology. They demonstrate that the planet is not as static as we once thought, and that seasonal cycles continue to shape its surface, creating active geomorphological features in an otherwise frozen landscape. Future missions with ground-based sensors may help solve the mysteries of these dark streaks. Until then, they'll continue to appear and fade, casting their subtle shadows across Mars's surface. Moving beyond Mars, the Sun itself hides secrets in its core. Beneath its surface, the Sun exhibits surprising internal behavior. These internal zones rotate at different speeds, with the equator spinning faster than the poles. Deeper still, there's an anomaly, a region where rotation changes abruptly. This differential rotation challenges our models of stellar dynamics and reveals new aspects of how stars function. The outer convective zone, where hot plasma rises and cooler plasma sinks, shows pronounced speed variations. The equator completes a rotation in about 25 days, while the poles take 30 or more days. But deeper in the radiative zone, rotation becomes more uniform. Between these two layers lies the tococline, a thin transitional layer where rotation changes sharply. This layer plays a crucial role in generating the Sun's global magnetic field, as the shear between the different rotational speeds helps stretch and twist magnetic field lines. However, the exact mechanics of this process are still under study. Observations suggest that the Sun's core may even rotate at a different speed than the outer layers, possibly faster. This challenges earlier assumptions about uniform solar rotation and opens up new questions about how angular momentum is distributed in stars. Heliosismology, the study of solar vibrations, has helped scientists uncover these findings. By analyzing oscillations on the Sun's surface, we can infer the behavior of its inner layers. This data reveals how the Sun behaves more like a fluid shell than a rigid body, with its internal rotation affecting everything from the generation of magnetic fields to sunspot cycles. Understanding these rotational features is crucial for predicting solar activity, such as solar flares and coronal mass ejections. These events can have significant impacts on Earth, disrupting satellites and power systems, which is why accurate modeling of solar behavior is essential for space weather forecasting. The Sun's internal rotation is influenced by convection, magnetism, and turbulent flows, all of which contribute to its dynamic behavior. While high-resolution models are beginning to capture this complexity, there are still many uncertainties. These rotational anomalies may not be unique to our Sun. Other stars also show signs of differential rotation, providing insights into how solar magnetic fields evolve. Studying these stars in comparison with our Sun helps refine models of magnetic field generation across different types of stars. The Sun's layered rotation is a key component of its magnetic memory, influencing everything from short-term solar cycles to long-term periods of low activity, such as the Maunder minimum. By studying these internal processes, we can improve our understanding of solar variability and its effects on space weather. The Sun's dynamic rotation shapes the light and storms that reach Earth, and understanding this silent ballet of plasma is key to predicting how our star will behave in the future. The Sun's magnetic field plays a vital role in shaping the space around us, yet we still don't fully understand its complexities. The sun is not just a source of light and warmth, it is a magnetic engine, constantly reshaping its environment through invisible forces. The sun's magnetic field governs the behavior of sunspots, triggers solar flares, and sculpts the solar wind, impacting Earth's magnetosphere, ionosphere, and even our climate systems. Despite its importance, the exact nature of this magnetic field remains elusive. Solar magnetism is generated by the solar dynamo, a complex interaction between the sun's rotation, convection, and plasma flows. This interaction produces a dynamic magnetic structure that reverses polarity roughly every 11 years. This cyclical behavior plays a significant role in space weather, but predicting how the field will evolve is still a challenge. Unlike a simple dipole, the sun's magnetic field is a tangled web of loops, twisted flux ropes, and open field lines. These structures become visible in the sun's corona, where magnetic loops trace the contours of the field. When these magnetic lines reconnect, they release massive amounts of energy in the form of solar flares and coronal mass ejections, CMEs. CMEs are among the most powerful space weather events. These massive bursts of charged particles are hurled into space, and if Earth lies in their path, they can disturb our magnetosphere. This disturbance can lead to geomagnetic storms, auroras, and disruptions to satellites and power grids. The magnetic connection between the Sun and Earth is not static. The solar wind continuously interacts with Earth's magnetosphere. When their magnetic fields oppose each other, reconnection events funnel solar energy into near-Earth space, energizing particles and driving electric currents. To predict these interactions, we need a better understanding of the structure and evolution of the Sun's magnetic field. However, our models are still incomplete. Spacecraft like the Solar Dynamics Observatory SDO, Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe provide valuable data. But mapping the Sun's magnetic field beyond its surface remains a difficult task. Recent missions are starting to probe the solar corona and solar wind in unprecedented detail. The Parker Solar Probe, which is approaching the Sun closer than any previous spacecraft, is collecting data that may help explain how magnetic fields are structured and how they drive the solar wind. The Sun's magnetism also plays a role in long-term climate patterns. While solar activity isn't the main driver of Earth's climate, variations in solar magnetism can influence cosmic ray flux and upper atmospheric chemistry. Periods of low solar activity, such as the Maunder minimum, may even correlate with colder temperatures on Earth. These changes, while subtle, are significant in understanding our planet's long-term climate trends. The heliospheric current sheet, a massive structure shaped by the Sun's magnetic field, also influences the flow of particles across the solar system. This magnetic equator is crucial in determining where space weather effects are concentrated, affecting deep space missions and astronaut safety. Despite decades of observation, many questions remain unanswered. How is the magnetic field anchored in the Sun's interior? How do surface features like sunspots relate to deeper magnetic flows? And how do small-scale magnetic events scale up to cause major solar disruptions? The Sun's magnetic field is a force of both order and chaos, influencing everything from auroras to satellite disruptions, while simultaneously shielding Earth from cosmic radiation. To truly understand the Sun's magnetic behavior is to gain insight into the forces that drive stellar activity. Turning to Earth's near neighborhood, we find something curious in space. There are areas near Earth's orbit that appear to be devoid of asteroids, and we still don't fully understand why. Astronomers expected a relatively uniform distribution of small bodies in this region, but surveys have revealed gaps, zones where few or no asteroids exist. These asteroid-depleted regions are found in orbital ranges that should be stable, and their absence raises questions about past disruptions or hidden forces that are still at play. These empty zones are located within the near-Earth object, neopopulation asteroids, whose orbits bring them close to Earth, often within 1.3 astronomical units. Despite detailed sky mapping, certain orbital ranges, inclinations, or eccentricities show lower than expected asteroid populations. Some of these voids remain even in high-sensitivity datasets, suggesting that something more than gravitational forces may be responsible for their absence. One possibility is gravitational clearing. Resonances with Earth, Venus, or Jupiter could destabilize certain orbital paths, nudging objects into chaotic trajectories or even ejecting them over time. However, the depleted zones don't always align with the expected resonant features, suggesting that more complex forces are at work. Another hypothesis is collisional evolution. If past impacts disproportionately removed objects from certain regions, they could have left behind these empty spaces. However, this would require unusual asymmetries in the rate of collisions, something that current models don't fully predict. Another possibility involves solar radiation forces, such as the Yarkovsky effect. This effect causes small bodies to slowly shift over time due to thermal radiation. While this could potentially push objects out of certain regions, the irregular patterns of these gaps make this explanation incomplete. There's also the chance of observational bias. Some orbits are harder to detect from Earth due to the viewing angle or background light. If these empty zones align with areas that are harder to observe, the absence of asteroids could be an illusion. Improved infrared surveys and space-based telescopes may help resolve this issue, but current data still confirms the persistence of these gaps. These voids may be relics of the early solar system, when Earth and Venus were still settling into their current orbits. Their gravitational interactions could have carved out these voids as they adjusted their positions, leaving behind fossilized gaps from this chaotic period of planetary migration. There's also speculation about past encounters with massive unseen objects. A rogue planet or a dense cluster of debris passing through the inner solar system could have scattered or ejected local asteroids. While there's no direct evidence for this, it fits with the observed selective depletion of certain regions. Understanding these gaps is not just academic. The distribution of NEOs is crucial for planetary defense. If certain areas are empty, it could mean that these zones are long-term stable, or it might indicate hidden paths for incoming bodies. This insight affects models for impact risk, as well as our understanding of how the solar system evolves over time. Monitoring these empty zones could reveal processes not yet included in current orbital simulations. Subtle gravitational interactions, solar activity, and interplanetary dust may slowly reshape asteroid populations, offering new insights into how the solar system is structured. These findings also have implications for the search for Earth co-orbitals, asteroids that share Earth's orbital path. The scarcity of such bodies suggests additional filtering mechanisms, whether through resonance, scattering, or thermal drift. These processes reveal a solar system far more organized and mysterious than it first appears. In the space between the planets, silence echoes in unexpected gaps, as if something once passed through and left only absence behind, not by impact, but by removal.